Okay, welcome to Industriuka 2021. A special welcome to everyone here in Elvespeilet. I'm really glad that you're here and that you're here in person. This event is also streamed live and it will be available as a recording. That's why all the talks today will be given in English. So a welcome to all you online viewers also. This event is organized by DigiPro, Cybernetica, Cognitwin Forsterk, and SINTEF. Let me start with some practical information first. There are emergency exits marked with green signs. You find toilets out in the hall under the stairs. And please register at the Brello app. You maybe have seen this QR code before. Register and you'll be able to see all the recordings live today and for the rest of the week. And you're also able to do a match on other with similar interest. There are match and speed dating tables out in the hall also. There will be a 1-hour lunch break around 11, and there will be 2 15-minute breaks, also with some food later in the evening. And after each talk, there will be some time for questions. So please raise your hand and spør gjerne på engelsk. I'll repeat, eller på norsk, I'll repeat the question. Okay, so let me start with a small story. I've been working in the software industry as a software developer for the last 25 years, writing code. That's many lines of code and debugging. And the common motivation between almost every project I've been involved in has been making businesses more competitive, more productive, more efficient, be prepared for future change, or deliver with higher control, or deliver with higher quality. Today, we call this digitalization. But the goals are exactly the same now as 25 years ago. But something has changed. What we 20 years ago spent a month to develop. Huh? I didn't click. I will soon click. Thanks. Please ask questions if you have anyone. That's very good. Thank you. So 20 years ago, I could spend months to develop something that today is ready as a component, a library, or even a product we could include in the solution. 15 years ago, we could spend weeks just to configure a database to be redundant across 2 locations. Today, this is available as a click in a checkbox. And if I click another checkbox, then the database is put in another continent. 10 years ago, security was for the few specialists. Today, it's in the DNA of every software developer. So things have changed. And to demonstrate this new world of technology, me and some colleagues in Bouvet decided to digitalize the process of getting a cup of coffee. We used all the buzzwords the software industry loves. That's IoT, it's AI, it's VR, it's ML, it's digital twins, it's data platform, and of course, it's the cloud. We built an intelligence coffee machine that would, just by looking at your face, it would know what type of coffee you wanted. And using an industrial robot arm, it would make and serve it to you. We gathered lots of data and analyzed it, searching for some hidden goal. And what was our takeaway from this project? Well, now is a good time to boost up your digitalization process. The technology is ready. And the coffee machine was placed in the canteen in Herøya, generating lots of interesting talks about digitalization. So having arenas where you can meet, discuss, and share and learn is a key factor to success. And did we get find some hidden gold in the data we analyzed? Well, you're likely to want a cappuccino if you're a female in your 20s, and if you're a smiling, bald man between 50 and 60, then you probably want a regular black coffee. Okay, so let's go back into today's agenda. We will start with a look into the future. Then we will hear about new arenas where the industry can meet, share, and learn. And after lunch, we will be covering and showcasing technologies used in digitalization. And at the end of this event, you will hear about an EU initiative that could be essential for your founding of your next digitalization project. Okay, so let's start the show. And to open this event, we welcome a former employee at Magnesiumfabrikken på Herøya, a former statssekretær i Olje- og energidepartementet, a doctor, and the mayor of Porsgrunn. Please welcome Robin Kåss.
Ja, tusen takk. Yes, thank you so much for the invitation to come here to open this event. And of course, welcome to Porsgrunn, which is the main center for land-based industry in Norway. And it's a bit bad for a seminar on digitalization. Then I have a paper manuscript, but I think but it was written on a computer at least. It was not handwritten. So we're moving forward in the municipality as well. But it's great that you've taken the time to visit us. We were recently awarded, together with our neighbor, Skien, to be the most attractive city in Norway to live. And NHO, the Norwegian Industrial Association, ranks us amongst the very best places in Norway to do business. And in that area, we rank especially high when it comes to competence amongst the inhabitants, the employees. Porsgrunn is a fairly young city, but we have a very interesting history. The old cities in this area are Tønsberg and Skien. Both are about 1,000 years old. But when the international trade started using larger ships, the great innovation of the sailing ships, then traveling up the river became impractical, and both Porsgrunn and Brevik developed as trading ports for the sailing ships. Then as a result of that, with the international trade, we got the first major factory, the porcelain factory. And then with the clean power from the hydroelectric power being transmitted down here to the ports, we got Eidanger Salpeterfabrikk, now Yara. And then more and more international investments that liked the great combination of having good supply of energy, good supply of cold, clean, fresh water, good port facilities. Also we have a limestone in this area, important for many of the industries, but also access to many people who were willing to work and to have and to take part in this great adventure. And I remember some years ago we were worrying, would all the industry go away to China? And now we have Chinese investors investing in industry here in Porsgrunn. And we see now it's a great business opportunity, this happening with the climate change. First of all, it's a great threat to the earth and to humanity, but it's also a great business opportunity. And like BioNTech did in Germany, 24th of January 2020, they thought, pandemic, let's make a vaccine. I think we together should think now this is a great, great challenge for humanity, and we can take part in solving it. And if you have the solution, to a great challenge, then that's a great way of making jobs and creating industry. We are very proud to be host for Industriuka. Norway needs to increase exports, and we can't be the cheapest with regards to labor or tax or have the easiest environmental regulations, but we can be the best. And I think this seminar is important because it links digitalization with the process industry. And to achieve our potential, this link is vital. And we're very proud that our local industry, and you hear more from Sverre later on, well, not in many minutes, how they have been in the forefront in this development. Process industries are a major industrial sector in Norway. And the main historical reason for this, and also into the future, is clean energy and extensive natural resources. They account for about 123 billion Norwegian kroner in export, and that's about 20% of our total export. Digitalization has been pointed out as an important enabler for future improvement and achievement of the green transition by introducing new digital technology and methods for automation and efficiency. More recently, Process 21 promotes digitalization as a tool for increased value creation and reduced emissions and waste. Areas affected by this are value creation, emissions reduction, reduced recycling, and energy efficiency through fulfilling the digitalization process of the process industry. The overall aim is to fulfill business targets such as social awareness, circular economy, cost efficiency, effective development, and you'll hear more about this in the program today. Key success factors are competence and cooperation. And for our city, our logo for the city is Sammen om Porsgrunn, together for Porsgrunn. And I think coming together, sharing our competence will help us to achieve these goals and to put this forward. So I wish you all the best for today and for the week. And I don't have it's digital, so I don't have a virtual thing to cut. And I hereby declare the Industriuka for open, and best of luck for today.
So, do we have any questions for Robin? It's not often the mayor is just waiting to answer, so here he is.
I'm glad to take one or two questions. Or for you.
Will you be returning to Herøya as a non-politic, just as an ordinary worker?
Yeah, maybe. No, I'm a company doctor on my spare time, but it's another company that's a competitor that's won most of the biddings for inside Herøya, but have some of the companies there.
Okay. Good. Okay, thank you to Robin.
Thank you. Ah.
Okay, let's give him a big applause.
And this is from Porsgrunn Porcelain, I think, when I see the wrapping.
Yeah.
Good. Local production.
Very good. Okay. Okay, let's have a look into the crystal ball. And to show us the future of the process industry, we have a speaker with broad international experience from technology development, digitalization, and execution of complex industrial projects. He holds a Master of Science in Mechanical Engineering and a PhD in Chemical Engineering. He's the Senior Vice President Technology in Elkem ASA, and he's the Chairman of Process 21. Please welcome Håvard Mo.
Thank you. Thank you very much for getting this opportunity to talk about the future of the process industry. That's quite an ambitious title, and I'm not going to talk about the future of all process industries, but what I'm going to do today is to try to make a link between the future we see for the Norwegian process industry and digitalization. So what are we going to do? We're going to enable zero emissions in a climate neutral society. I've, is it a pointer on this one or no? I've divided my presentation into 4 parts. First, I will give an introduction to Process 21. Then I'm going to show you some examples of climate targets communicated by selected industrial companies. I will elaborate a little bit on what it takes to get zero emissions in 2050. And then I will spend between 5 and 8 minutes at the end to say a little bit about the role of digital in the transition of the process industry. So, Process 21. Process 21 was launched in 2017 in the governmental white paper about the process industry in Norway. We started up in 2018, and we delivered the report this year in February to the Prime Minister in an event organized here at, or not here, but at Herøya. What we have done in this work, and probably will continue, is to give strategic advice and recommendation on how, to the government and other actors, on how to combine sustainable growth and reduced emissions from the process industry. The framework for Process 21 is really the zero or net zero target in 2050. And if you look at the different target set, we have the Paris Agreement with a target to limit global warming to well below 2 degrees, preferably to 1.5 degrees in 2050. And then we are looking forward to see what's going to happen in COP26. In Europe and Norway, we have the target has been raised, or the bar has been raised, and more ambitious targets has been defined in 2020 and in 2021. And the most recent target that has been proposed but not yet been decided is the Fit for 55 package submitted by the European Commission to the Council and to the European Parliament. And if this follows the ordinary legislative procedure, we expect to see a decision in 2023. China is also speeding up on the transition. We're seeing now recently a decision to stop international investments or investments in coal outside China from the Chinese government. Process 21 represent a knowledge base that will be valuable for the next 5 years. We did deep dives into 10 different topics. We bought 4 additional reports on selected topics, updated the roadmap towards zero net emissions, and put this together into a main report early this year. The 10 expert reports saying something about the future is on entrepreneurship and product development. Quite a good report on bio-based process industry. We have circular economy, carbon capture, carbon utilization, and new process technology. 1 report on digitalization, foreign investments, competence, supplier development, and power market. And especially now today with the challenge that we have on the power price, the power market report has been I've been invited several times to give presentation about the future power requirements. In Process 21, we focused both on 2030 and 2050. The mandate was 2050, but it's not possible to do something in 2050 without being successful in 2030. And it's also good when you're trying to put up a perspective on the future. If you look 10 years into the future, you should look 10 years back. And if you look 30 years into the future, you should look 30 years back. And if you see the transition that is going to happen the next 30 years, it's going to be much more and much more comprehensive than what we have seen the last 30 years. In our report, or in our work, we looked into, for the 2030 perspective, we looked into, well, product development. What kind of products do we need to deliver for the next 10 years? How will the value chains change? how will digitalization play a role? And there's also a fact that if we want to reach zero net emissions in 2050, we need to decide on the technology in 2030 before 2030 because of the lead time we have to develop the lead time needed to develop new technologies, pilot them, and build the future industrial plants to actually have net zero emissions in 2050. Some reflections, and I think these reflections are being strengthened by what has happened on the global basis over the last 6 months. If we want to make a transition to a carbon neutral society, then we will have to also have a fundamental change of the process industry. Approximately 20% of the global CO2 emissions are coming from the process industry, and that has to go down to zero by 2050. And we need technological breakthroughs to convert the process industry from fossil fuels to renewables. What we also have seen over the last 2-3 years is that the customers are now starting to require more and more documentations on our carbon footprint. We will not be able to sell in 2030 without being able to document the carbon footprint of our products. The last quarter, we have seen spikes in raw material prices. Fortunately for the process industry, some of the finished good prices have also gone up, and for some companies, even more than the raw material prices. But with an increase in the cost of natural gas of a factor of 6 over a very short period of time, that tells us a little bit about the volatility that we see today because of mismatch or challenges with the supply chains. And personally, I think that we will see even more or bigger spikes in the future. We also see that investors require full transparency on climate change-related risks to better secure their portfolios. In addition to the challenge with climate, we see a US-China rivalry, and we see that Europe is targeting strategic autonomy. So what does this mean for the process industry in Europe? It tells us that the time where China should be the low-cost producer of all commodities and some specialty materials that has passed. And we will see that production will be in Europe to serve the European market. If we then look into the climate targets communicated by selected industrial companies, the first climate target is to be relevant for the future. Sustainability is about making money. If you don't make money, you will not be there in the future. So the first thing a company should do before they look at the climate strategy is to ask if they have products that are actually attractive in 2030 and 2050. This is an example from Elkem's climate strategy. I will not go into detail on that, but what I could say is that for some of the products we're talking about, we are seeing growth per year up to 15-20% because we have the transition in the economy. Then these products have to be delivered with a documentation on the carbon footprint, not only on the direct emissions and the emissions related to power, but also the emissions related to the raw materials and everything that we put in when we produce the products. The Greenhouse Gas Protocol asks companies or require companies to report absolute emissions. But if you look at the customers, they would like to see intensity ratios. What are the tons of greenhouse gas emissions you're emitting per ton product produced? One example here is again from the company where I'm working. We are seeing now a growing demand on low CO2 silicon, where the customers are asking us to deliver silicon with a documented carbon footprint and with a supporting LCA. Hydro is seeing the same on aluminium. And then the emissions. From an engineering point of view, if you have zero target, you would say, let's do a fixed percentage in reduction every year. That would be the dotted blue line. Then you have the financial approach, linear decline. That will be the dark blue dotted line. And then you see the two, one yellow and one orange line. That is the targets defined by EU towards 2020. The existing target with the upper yellow line. And then you see the line we expect to see if Fit for 55 is decided. The process industry in general is a little bit behind from 1990. I've used 2005 because that's really when the ETS starts, and it's flat from 1990 to 2005. Some reduction from 2005 to 2020. Then you see most companies, they have a 2 degrees, or several companies have a 2 degrees year on year, at 2% or 2.5% year on year reduction. And then with the dotted yellow line, you see that what we really have to do from 2030 to 2050 is a steep reduction. And that is really a big challenge. So take some Norwegian companies, or at least companies located here at Herøya, Eramet and Hydro. Both companies have quite ambitious target, Eramet 40%, Hydro 30%. They have defined different time periods. So in practice, it's about an absolute reduction of 2.5% per year, which is in line with less than 2 degrees target, but not according to the 1.5 degrees long-term temperature goal. So how do we get to net zero emissions? If we take a systems perspective, I thought you would like this better than trends about GDP growth and things like that. This is more technical with the audience here today. So this is a production process in the process industry. We have industrial processes with metal production, calcination for cement production, plastics or polymers. Hydrogen production is relevant here at Herøya, and we use a lot of heat. Many of these processes are emitting CO2 either directly or indirectly. Polymers, they emit CO2 when they're being produced because of heat is being used, but a huge part of the CO2 emissions are really downstream when the products have been used and they are deposited or burned. The problem for the metal industry is that we are in the CO2 emitting business. So even if we are using renewable energy, we will still have challenges with carbon being used as for carbothermic reduction, where we remove oxygen from metals by using carbon. Then we have the conventional way of decarbonizing the process. We could start with scope 1. That would be carbon capture and storage. Or we could use biocarbon. If the biocarbon can be documented as carbon neutral, we will then emit biocarbon that is part of the natural circulation of carbon in the atmosphere. We need to use renewable energy in our process. We also have to look into the other consumables we have. Then we get the products, and for the products, we have to look into how we use them. What is the effect when they're being deposited or when they are being used as input factor in new processes? And then, of course, to do the recycling when you have carbon in your products is really important. And the ultimate solution will then be to have a CO2 for metals is to have a CO2 or a carbon-free production process based on renewable energy. For metals, we are seeing some development. Steel, which is the biggest emitter, is trying to use hydrogen, and HYBRIT is a joint venture between SSAB, LKAB, and Vattenfall, who is actually using hydrogen in the production process. If this is going to work, and it works, at least at a small scale, we need access to a huge amount of fossil-free electricity to produce the hydrogen needed. Unfortunately, I will not go into detail on this one, but unfortunately, only the metals up here with or with the low at the upper part where we have a relatively small Gibbs free energy in the reaction can use hydrogen as a reduction material. For the other processes, we need to find other ways of producing the metal. So we have a big challenge for the process industry. Some processes can be decarbonized either by using hydrogen or by conventional methods. But what is really needed for the future for the process industry is to find new and innovative ways to produce these metals and other products from the process industry without emitting CO2. So what is the role of digital in the transition? Digital is not the solution long term. Digital will be an enabler long term, but it has to be combined with fundamental work. So if you look at 2050, the new production processes will most probably be high intensity processes with high raw material yield and the ability to take advantage of rapid changes in power and energy prices. Of course, to do that, you need a good digital framework around your process. You need instrumentation, and you need advanced process control and optimization, everything you are working on today. But we also need a change in the production process. However, we will need the same products or digital solution today, but a little bit more developed. And what we should focus on in digital is to deliver or develop ourselves towards 2030. Because what we're going to use in 2030 and moving forward are the products that we have, and they will be further developed to support and control the future production processes. So if we look at the role of digital, what can we do? We have to look at digital marketing and sales and services. We have to look at highly automated and optimized processes. We will need automatic reporting of environmental KPIs. And we would need digital solutions for supply chain and logistics monitoring. Several process industries or industrial companies have defined digital roadmaps where they're looking at all elements of the digital transformation. If you compare companies like BASF with the Norwegian companies, we see that the Norwegian companies are not as advanced or ambitious. I would assume, looking at this group, most of you are working on digital solutions for production optimization. How can you monitor the process and how can you optimize it? If you would like to take advantage of digital as a total package, we have to look at not only at cost reductions and improved processes, we also have to look at the customer experience, and we have to look at the value chain optimization. One thing that is given is that we need digital solutions for future stakeholder requirements and also to be able to optimize on the circular economy. So both on product reporting and tracking of products in the value chain, will require new digital solutions. Today in the program, we will get a lot of presentations about how we optimize the production process. I like this illustration by McKinsey. It's quite simplistic, but it gives a good picture about objective function. It's really about where you have the big circles. It's where you should focus your solution to support a certain process industry. So a big dot tells you that you will probably have a big potential for improvement. And in Norway, we are quite good at this. At least we were. I mean, Herøya with the research center of Norsk Hydro in the 1980s and early 1990s was really top-notch. Personally, I did my PhD at that point in time. Personally, I think we have fallen a little bit behind. We have not been able to renew ourselves in Norway. We are lacking. We're lacking on instrumentation, or we should do more on instrumentation, and we should also take into consideration the speed or the time needed to implement, to be more quick or be able to do more rapid implementation and work, well, the buzzword is agile, but at least learn, improve, and then make the solutions better. One area where we actually need, or we really need to improve is on the front-end side towards the customers. If you compare the process industry with the music industry, the companies or film industry, Netflix, the companies that have been able to reach out to a huge amount of or large number of customers are the ones really winning. And this is an area where the Norwegian process industry has not been as ambitious as international competitors. We have good examples like Yara, but Yara is only one out of many companies, and I think this is an area where we really should improve to be relevant in 2030 and be in a position to actually make money in 2030 to reach zero net in 2050. So, to summarize, the transition to a climate-neutral society would require a fundamental change in the process industry. Digital will play an important role to secure the competitiveness and support future stakeholder requirements towards 2030. And this is also, to a great extent, the platform that we need to move to 2040 and 2050. Decarbonization of the process industry by 2050 requires a combination of extensive industrial R&D and significant expansions in renewable electricity generation. For the Norwegian process industry, I would strongly recommend to work on raw material utilization or also because we don't have the scale effect in Norway, meaning that we have to be even better than our competitors. If you look at long term, all the materials that are needed for the transition into a zero net society will come from the process industry. We're talking about future advanced materials. And the companies able to combine product innovation and decarbonation of their production processes represent the future of the process industry. That's all I had in my presentation. I'm happy to answer any questions you may have. Thank you.
Okay, so that was an interesting talk, giving quite a direction for us. Do we have any questions? Did you understand the equation, the chemical equations, everyone? Simple? Okay.
They're not balanced, so but they will be very complex if I balance them out on the stoichiometric basis.
Okay. So are you all ready to do this transformation? It seems like you advise to do a fundamental change in how we produce our product. It will require a lot of research and development. So we have quite a big job in front of us.
Yeah, the 2030 target, I think most companies will reach them, not a problem. But really to get down from where we will be in 2030 down to 2050, that represents a major challenge for the process industry.
Okay, thanks a lot.
Yeah.
Okay, I'll give you a local gift also.
Thank
Here
you.
you are. Okay, big applause. Okay, so our next speaker, I'll start with Old Norse expression. Seider, et gammelt norrønt uttrykk. And the meaning of that is it describes the magic associated with predicting and shaping the future. And the magic is going to happen here, in Porsgrunn, in Grenland, og I Herøya. Our next speaker has been involved in innovation and R&D for years. He has wide experience as a board member in leading technology companies. He has been chairman of Norges Forskningsråd and now the chairman of Teknologirådet. Please welcome Director of Herøya Industripark, Sverre Gotaas.
Thank you. Probably used. Welcome, everyone. It's a pleasure to see so many clever people here in Porsgrunn. We have a lot of those before, but we also always like to see someone new. So I go to get into some very exciting ideas we have at Herøya and show you how we can help with what Håvard told us about. We are now entering a period of change. We need competence and we need industrialization. So this is what Seider is about. We have a big work to do. We're trying to decarbonize this fantastic planet we are living at. I don't think all of us have seen into what it could happen here if we don't take the steps forward we have to do. The IEA has some predictions. This is one of the ways they are saying, how can we get to a zero emission? And of course, there's a lot of pathways to do to that, but that's a very one concrete one. By taking these steps, IEA says you don't need to get more oil. You don't need to get more gas than we already have. And that's one of the main issues. So I'll take this as a start and show you. Here in Grenland and Herøya, a lot of companies are already working in this direction. This is an example of some of the companies in this region and where they are focusing to reach that zero emission goal. And why do they do it here? Well, probably because they are here. Some of them are coming here because the infrastructure is good, because the competence base is good, because people here are used to work with complex industrial processes. But we also have a very broad and very brave goal in this region. We have said we are going to be fossil-free or carbon positive in 2040. That's 10 years before 2050. Someone have to lead the way, and this region has said that will be us. So all these projects, these dots you can see here are identified projects that is possible to reduce the 2.5 million tons of CO2 we emit today down to zero in 2040. Well, not exactly. The gray scale is the emission we don't have any answer on yet. And that's the main focus for this area here. We can take care of all these projects we have identified. We have the technology, we know approximately how much it will cost. Some of them are not financially available yet, but there might be, there will be. But the green area is where we're going to put our strength. If we can solve these 500 kilotons of CO2 emission, it's not only this area that can use it, it will be a world changer. We can do it for the world. So that's the main focus, and that means we need new competence, new knowledge. We need a lot of new solutions that we don't have yet. So what are we going to do? That the Herøya Industrial Park is not a big organization. We can do this, but we can put things together to help doing it. And what we are trying to do is to connect the building on the right hand side, which is the research park or Herøya Industrial Park, with the left-hand side, which is the operational part. And you can see the factories in behind. And that's what Hydro is all about. As Lars-Erik said, Hydro is some kind of magic. It's some kind of predicting the future. It's some kind of getting a hint of what's going to happen, to pursue it and see how can we do something about it and make this happen. That's the idea of Hydro. Hydro is not a building. Hydro is not a place. Hydro is a concept. It's an idea. But it can be shown as buildings, as ideas, as ways of working. So what we are literally doing is to connect those two elements, the research park and the operational part, with a bridge which are trying to ease the way from ideas, from new competence on this right side into operational use. So in this area, Hydro will look more or less like a building complex, and that's just to visualize it. And what are we doing? Well, a building, well, that's nothing. We're trying to fill it with something. And the first thing we are doing is to joke a little bit with ourselves, because Herøya, as a former Norsk Hydro plant, has its own geographical coordinates. Herøya North is not world north. So when I stand in the buildings in Herøya and point north, it's not north. Herøya North is the building over there. The rest of the world has north that way. So what we are trying to do is transform this industry, being here for almost 100 years, working in its own way, try to transforming into connect to the rest of the world, by literally build a building to show it. So that's one of the ideas by this building. We are trying to reach out for the rest of the world, just not only to get help from them, but also to help them back. And of course it will look nice. It will look like a very nice building. And what do we put into this building? We'll put anything that can help the researchers. We have more than 400 researchers in that research park at the right side of the building. Put anyone that can help us to transform this new knowledge into operational use. It might be DigiPro, it might be research institutes, it might be companies in digitalization, whatever. We are creating a space where all these companies can come together for longer or shorter time to make solutions, to transform this new knowledge into use, because that's the main challenge. We are moving into areas where we don't know the answers. Well, we have always done that, but now it's very, very viable to see that we have to find these solutions. And this building is one of the ways of showing that. And I can exemplify that with something you all know about. It's a TRL scale. As you know, that's a way of showing how mature is an idea, how mature is a product, how mature is a solution. And you start in the very lower end. TRL1, well, you might have an idea, you don't even know what it can solve. Just basic researching. And on the other end, you have a verified product, you have a verified process, which you can put in production, which are industrialized. And this area has been used to do this. As Håvard mentioned, the main research unit for Norsk Hydro was on this place for many, many years. And I did actually that. We have a joke saying, you made new solutions before lunch and implemented after lunch. It was possible as long as you were at the same business. But we are trying to recreate that one, to make a continuous line between research and industrialization. So what we are trying to show is that literally we are trying to connect the low levels of TRL with the high levels and implementation. We as in the industrial park does not create solutions. We do not do research. We do not have the answers. But we can help making them. We can make it possible to find them. And that's the main idea with this CIDR concept. That's the main idea that a lot of companies already has raised up and said, we will take part of this one, and this will start being working with early next year. So I invite anyone that have an idea how to move any new knowledge into industrialization to team up. Not necessarily to move into that CIDR concept, but be a part of it wherever you are. This is not a location. This is a concept. This is an idea. We will show how it could be on Herøya, but we do need everyone in the total Norway, in Europe, in the world to help us to reach this. And so please come up, team up behind this concept. We are here. We are ready to step into the future. Thank you.
So, do you have any questions for Sverre? It's a really okay. Yeah, I could repeat it, so the online viewers will get it also.
No, I was discussing over breakfast this morning about how to get big impact. Okay, so I understand with respect to the industry part, but also the impact to the local community. I mean, we have the mayor here. Are there plans to try and also link that part? We have a lot of the technology development, but in the end, it has to end up in the society in a way. Are there any ideas about that, about how to make that link?
Okay, so so the question is, how could we also link the final product and link to the society around us? Is that possible? How could we do that?
It's not only possible; it is necessary. We don't live in a vacuum. The industrial park or the industry itself is a part of society, and all solutions we have to find, which we haven't found yet, will have to be implemented into the society. We can't do it in the industry as well. So this will also be a part. And there is the University of Southeastern Norway, which is located here, will also be into this center with a lot of different, what do we call it, faculties, not only the technical one. So we will look to find actors that not only look at technical solutions, but also how to implement it into the society and how the society can use this to get their own problem solved. Because, as I said, we are not living into a vacuum. We have to implement everything with respect to how the society is going to take care of it.
Okay, thanks. Ok, så tusen takk, Sverre. Dette her blir veldig spennende. Takk. Okay, now it's time for lunch. It will be about 1 hour lunch break, maybe a bit longer. The food is not quite ready, I hear. So you will have time to discuss and talk a few minutes before the food is served out in the hall. Okay, so see you here at 10 minutes after 12. We will continue with the next, and then it will be Frode Brakstad. I will talk about DigiPro. Looking forward to that. Okay, thank you. Da starter vi om 1 minutt. Okay, welcome to part 2. Hope you enjoyed your lunch. And I'm glad to see that you are a bit closer. That feels good. Okay, so what if we gather all the big players in the process industry and the most experienced R&D actors and the leading technology companies, and we use that to drive the industry into the future? Well, that is exactly what our next speaker is doing. He spent a lifetime doing data analysis and process optimizations. He's a chief scientist at SINTEF. Please welcome manager of DigiPro, Frode Brakstad.
Thank you, Lars-Erik. This is the first slide, yes. The title is National Center for the Development of the Process Industries. And that is, in that title, I will say that that is also a vision, because today I will say we have a meeting place, very interesting meeting place for digitalization of the process industry. But in this presentation, I will tell a little bit about what this center is, why we have this center, and how it works. What, why, and how. Starting with what, we are a meeting place for process industry, R&D institutes, and technology providers. And then we try to cooperate with other organizations that has process industry and digitalization as an aim. And we want, of course, to develop this center to have a kind of national impact. That's very important. And so far, we started January this year, and so far we have roughly 25 members from industry and R&D institutes, as you can see here, and clusters. And we have the technology provider that is very important for the process industry as well. So what we have started with this year in January, we had 2 larger conferences where the industry presented their needs, and then we got this list of what they said was most important for them. And this is social awareness, circular economy, cost efficiency, and effective development. And then the challenge is to understand, because digitalization is a critical factor and it's an enabler to reach these targets. So to understand what is really the red thread here for digitalization, that is something we discussed with the industry. And they told us that predictive maintenance and autonomy is one such field. So we started with that one, and we defined 4 areas that was of most interest for the industry to cope with predictive maintenance and autonomy. And we come up with sensor technologies from one very important area, and advanced data analytics, communication network intelligence, robotics for autonomy, lean digital competence, and project portfolio. So far, so good. And then we had a lot of workshops, and we come up and defined working areas for these 6 fields. And we defined, of course, KPIs to track the process. So we are in that process now. And to answer why, that of course, that few, if any, companies have all these competence in-house. Also, we discussed then, and we did cooperation and communication. We found roadmaps that was very generic, I would say, and we prioritized these working areas together. And then, of course, very important, we share experience and competence. We develop competence. We boost innovation, and we have joint developments and shared cost, fast implementation, and we share technology. So this is, I think, answer to why. And how? Well, communication is very, very important. So we communicate then between the industry, technology partners, and our R&D partners. And we have defined these working groups where we have members from all three segments, from industry, technology partners, and R&D partners. They are working together with the persons here leading the 6 areas. It's a model working very well, I think, to be honest. And then we have defined so-called drivers for creating value. We have the exploit part of the projects. That's very, very important, where we look into our products and see what is made of technology. Can that be exploited by other of the partners? So-called low-hanging fruit, very important. And then we, of course, have the explore, where we need new knowledge. Then we initiate R&D projects. And, very important, organizational competence, lean digital, and EVU courses. Etter- og videreutdanningsprogram. That is also to answer on the process 21's expert group report on competence, that having and develop competence is very, very important for the process industry to get this digital transformation as needed. Yes, and we have some projects that we now say that so-called spin-in projects. It sums to a little bit more than 200 million, where we, on regular basis, communicate and discuss and present results. And this event is a part of that, because we will later today hear more about results achieved in the Cognitwin project. We also have a Die4U, a similar project, and we have self-adapting model-based systems, where we have 7 process industries working with yes, self-adapting model-based systems, and where Bilfinger is the lead. And also we have towards autonomy in process industries. Very, very interesting project, where we try to find what can be transferred from developed technology. These one are new projects that DigiPro has generated then from summertime until now. And it sums to roughly 360 million Norwegian kroner. The first one is a zero-defect manufacturing with human-machine collaboration for optimal sustainability and productivity. Yes, that is CEDI. And then we have Cogniman, enhanced robotic systems. These two are the two that we have sent for the Horizon Europe. And then we have 3 projects toward the Norwegian Research Council. Connect, Capacity Lift, Indigo, and the last one is a National Competence Initiative, what we call Phase 1. So the last one is a national project. The next last one, Indigo, is also a national center where we try to build pilots for testing new technology, and also to work with scaling of new technology. So the 2-letter one is in fact a step we have taken from towards being a national center. So we will see then. These are applications. We got feedback, I think, end of this year. So, and also to share some of the communication, we have our website, and you can memorize this one maybe, digiprocenter.no. Then you can come in contact with us if you want to become a member, or if you have any other questions. Yes, that is very important. And also we have an exclusive site for members, where we can go back and have a look on, we try to record all events, so we can have a look on what has been passed. So we have digital twin solutions, we have thermal imaging and image processing. We also have some environmental issue with gas and particulate emission in industrial environments and so on. So I think this is a benefit for the Norwegian industry. And so far we have started this center. We have run it now in 10 months. I really look forward to continue with working with this center. We have a lot of fun, and we have a lot of sharing competence, and I think this is valuable center, and be more and more valuable as years comes. Thank you for your attention.
Okay. Thanks, Frode. It was an impressive list of applications you had there. And do we have any questions for Frode? Well, I assume that you didn't have, so I prepared one. And so, what do you think? You have only been running for 10 months. What do you think is a key factor for your success for the next years?
I think the most important is now to convert this project to something operational that gives the process industry a value, because that is the key for this center, to give the process industry value, or else we will not be there in some years. So that is one critical thing. And also I feel that such a fantastic center, we need to market it and become and to have much more members. These two, I think.
Yeah. Okay. Others? If not, as usual, Frode, we have a present for you.
Oh.
So thanks a lot for your time.
Thank you.
It's not many words I'm saying, but I can't memorize them. So our next speaker, he has a background from computer science and system engineering. He has spent more than 20 years at Elkem doing automation and digitalization. He is now in charge of test and piloting facilities at Elkem. It will be really interesting to see his view of DigiPro. Please welcome Director R&D Technical Center at Elkem, Trygve Hansen.
Thank you for inviting me to speak about our views on DigiPro. Frode has given a great introduction to both how and why, and I'm gonna put a bit emphasis on the why. So what do we think about the potential with DigiPro from an industrial perspective? So looking back at the beginning, Frode already covered this, so I won't spend a lot of time on it, but we had a very interesting workshop at Herøya in 2019, preparing for an SFI application. And we discussed these things, what should be the most important values coming out of a project like that. And obviously we are talking about increased output from production and reducing resource consumption, but also increasing safety and increasing margins in production. We went forward from the SFI application to actually establishing DigiPro as an alternative to the SFA project. And we needed to address some of the biggest challenges in our industry. Of course, we have a lot of challenges, but some challenges are more important seen from a digital perspective than others. So we wanted to imagine a future situation where we had more smart production, autonomous production. And to achieve this, we needed to overcome the challenges with the low observability we have in our processes. automating our processes is not a straightforward thing. We have some challenges when it comes to complexity of the processes and also harsh environments that doesn't allow us to introduce instruments and sensors inside our equipment. And we also struggle with a low instrumentation level on our equipment in general. I think this is common throughout the industry. So getting enough data and becoming advanced enough in terms of using advanced analytics and model-based approaches to controlling the processes is obviously some core challenges that we needed to address. But these are technical challenges. We also wanted to discuss the challenges we have regarding scaling technology. I think most of our industrial players will agree that to at least some extent we are very good at experimenting with new technology, doing development and research on digital concepts to improve our production. But going from R&D into industrialization and actually capitalizing on the technology is another story. That's not so easy. And then we are not only talking about technology and the technical challenges with the digital concepts, we are also talking about the humans, the organization, and the cultural part of the company. So these things go hand in hand. We need to both address the technical issues and potentials, but also to look into how to scale, how to move from experimenting with the technology and actually implementing things in production. And of course, competence as well, a very important part of this, because having enough insights in how to do things, both when it comes to R&D, but also when it comes to executing the transformation, we need competence. And I think we need to address also these cultural elements that I mentioned. For instance, how do we involve our process engineers and our operators, making them stakeholders in this? Because we know that it's very hard to implement new technology and make people change their way they work today. Another element is involving the technology providers, the suppliers. How do we involve them early enough when we develop and verify new technology concepts? When I speak with other industrial players, I get the same feedback from everyone, that these are challenges that we need to overcome if we want to be in the forefront when it comes to digital transformation in the production. And I also get the feedback that we can't manage this individually. The best way to address this is to share experience, identify projects, and work together to overcome this. And that's, I think, is the most important foundation for DigiPro. So looking from an ideal point of view, like I said, we want to have a situation where we have smart production, autonomous production, or smart decision support systems that enables us to optimize production. This is taken from an example in Elkem. It's a project with funding from Norwegian Research Council, developing what we call a smart furnace. It will be a decision support system that takes not only the data and the digital twin of a process, but combines it with physical models, because it's so hard to get into the furnace with measurements and instruments. So this is quite advanced. And what we want to achieve, what is a good situation here, is that we get a predictive decision support system that enables our operators, our process engineers, to take the right decisions at the right time. And you see the business case here with a possible reduction in energy consumption. 170 gigawatt hours is estimated. There's a lot of potential here. And here we are not even talking about a fully autonomous system or an advanced process control system. We are just talking about improved decision support. So the potentials are huge, but the challenges are also big. And we need data, not only the models, but we need more data. We have too few data. And to develop instruments and to develop sensor concepts, soft sensors, etc., we need to develop new concepts. And we have a lot of examples on that, also with DigiPro. And there are some great opportunities out there. When we look at the market and evolvement of new types of sensors, photonomy is one area with a lot of possibilities, use of cameras, vision systems and stuff like that, obviously. Lasers, and a lot of more areas than this. And we look at one of these now with the DigiPro, an instrument called the LIBS, laser-induced breakdown spectroscopy, which gives us the ability to study the chemical elements of a material, the surface of a material, online. So instead of doing manual samples on a material, we can have an online continuous measurement of the chemical elements. This has been proven for instance, in aluminium. It's also even been used with molten metal. So the instrument itself is quite mature. But using this on our processes is not a mature thing. We need to develop an understanding of the instrument and also investigate the potential uses of the data, like I said, into an improved decision support. We can probably imagine this being used at many different types of processes. For Elkem's part, both upstream and downstream from the furnace, but also on the furnace. So it has a huge potential. It can support advanced or more, as we see, advanced decision support, but also advanced process control if we want to take out the full potential. We have some challenges with the instrument that we want to look into, and this is why we have the LIBS project. To understand how we can use it on different wavelengths, and if we are able to combine different wavelengths in same instrument. Of course, homogeneity of substances is important because there are some limitations when you look at an instrument that studies the surface of a material. And also the robustness and the calibrations and validation of the measurement data as well. So this is part of the coming LIBS project with DigiPro. So that's just an example. And of course we could discuss many examples, many potentials. And I believe when it comes to the application of the LIBS instrument, we are at a lower TRL level. Sverre talked about the TRL levels. And this brings us to one of the challenges that I mentioned. How do we scale the technology? We will go through the first phases here, or the first levels of maturity, investigating the use potential of the instrument. And we will, I'm sure that we will get a good result from that. But at some point, we will also scale this technology, implement it in production, and capitalize from the technology development. To be able to do that, we have to address those issues I mentioned around how do we involve operation early enough, and also can we involve our suppliers in a better way than we have done before when we have working individually on projects like this. Now we do this in DigiPro Regie, and this slide here I borrowed from Hydro. We have been discussing this exact challenge. How do we now involve suppliers early enough to help us overcome the gap between R&D and industrialization? And also, as you can see on my other side here, we have to take the whole life cycle into account, because we want not only to demonstrate the technology used in operation, we also want to take care of the whole life cycle of the technology. So the interesting thing is that the suppliers can help us on both parts, but the the prerequisite is that the supplier is involved early enough. And I think DigiPro is one of the arenas that can make this possible. And we, as Frode said, we have applied already for quite a lot of money on 6 different projects. We're talking 360 million NOK. And Connect 4, you see here, is the LIBS project. And when I prepared for this presentation, I looked at these applications and I asked myself, will these applications, if we get approval, will they support those important challenges that we need to overcome? And I think they do. They also cover the competence part. And it's quite interesting. Frode said we have fun, and we do. It's interesting because we can play around these challenges and discuss challenges. We recognize the same challenges and also the same ambitions. So to be able to work on a portfolio like this with DigiPro is a unique possibility in my mind. And this is exactly what we do. And it's not only the competence at SINTEF and experience in the industry, but of course it's the technology partners that we have, and not to forget the clusters as well. I believe from only, I would say, a year of operation with the DigiPro, we are off to a good start, and we are already see some of these synergies that I'm addressing here. So that was my presentation. I'm happy to answer any questions.
Okay, so how do you go along if you want to you see all this application and you want to start? What's the first step we should do?
I said to the board, a board meeting we had in June or around June, that now, if we, as I did, I look back to 2019 when we started DigiPro, or the SFI part. We have been working, at that point, we had been working for a year preparing all this, and now the proof of the pudding comes. Are we able to establish these projects and actually creating value from the projects? That is the next step, and is also the main focus for the project board of DigiPro.
Okay, yes?
So since you touched a bit on the challenge of bringing the research into real operations, have you managed to do something like this? Have you managed to take some research and actually use it in your everyday operation? And if yes, how did it go? And if no, what can we, the people coding the algorithm and everything, what can we do to help you do this more?
Okay. Good. So the question was, have you done any research that you've implemented into the operators, and how did you succeed with that, or do you see any challenges with implementing the research you have?
Yeah, so I think your question is straight to the heart of the problem. We have to admit that we have a lot of unsuccessful investigations into that. We know that we are not able to scale often, but we do have examples where we succeed. And in my opinion, one of the most important reasons why we succeed in some examples is the way we involve our operators, our process engineers, in an early phase. Not only for the ownership, the sense of ownership, but also from the fact that we are changing the way people work. We are changing, we are influencing the culture, and we need to take that into account. I think that's a key observation the few times we succeed. And you also asked about how you can support this to improve this. And then I would like to refer to what I talked about in these lower maturity levels when we work on technical developments, not implementing, but actually developing the technology. Like I said, we need to have a closer cooperation with the technology providers, not only the brilliant competence that SINTEF and others hold, but also the actual technology providers. And I also, as I also said, this is especially interesting because the same providers can also enable a full life cycle management and getting results from that as well for us.
Ok. Da gjenstår det bare å si tusen takk.
Thank you.
Veldig bra. Takk.
Thank you.
Okay, so one of the challenges Trygve just talked about was competence. And our next speaker, he has 25 years of experience from Hydro. He's passionate about developing people and organization in the process industry. And his key tool to this is competence. He is manager of the expert group on competence in Process 21. Please welcome the head of organization development at Hydro Aluminium Metal, Per Holde.
Thank you. Thank you. Thank you for having me. I think you exaggerate a little bit. I just had 24 years. So a slightly exaggeration. Yes, my name is Per Holde, and I'm going to talk about what always complicates technology people. So, first of all, the future of process industry is about competence, definitely. I mean, we're not really making new doors, but go into open doors at that respect. And competence was one of the expert groups in the Process 21. There are two very easy outcomes of that. And the first one is that sustainable growth in the Norwegian process industry is not possible without enhanced competence building. And sometimes we brag about our competence in Norway. I think we have quite a lot, but competence is like the more you know what you don't know too. So we need a substantial competence building in Norway for the future of process industry. And this building has to be in close proximity between and a committed collaboration between industry, between educational institutions, research bodies, and governmental institutions, both at national and regional level. I I'm really expecting that DigiPro could be a kind of arena that could gather some of these players. I think Frode mentioned, and Trygve also did that, mentioned the initiative that is on the further education level for engineers that we have applied for, and that I've heard that we will get that from the funding partners. And there we have brought together the universities of Agder, the University of Southern Norway, USN, two parts of NTNU, both the Gjøvik part, which is security, is about data security, and the industrial economy in Trondheim. We have brought them together, and we have brought together with industry partners and made a common application for further educating the process engineers in our industry. I think that's a very promising and first step and in making DigiPro also an arena for competence. Process industry needs to be more attractive too in Norway. I think this picture is not far from here. Hopefully there are none of you on this picture, but it's some years ago. I think it's important for us to say that we are not riding into the sunset, the process industry in Norway. We are still performing well, and we have a big future in front of us. We need to underline this, we need to brand this, we need to tell students this, we need to tell the pupils at the schools that too, that because many still perceive process industry as dirty and backwards looking industry. While the sustainable future is somewhere else than in process industry. A lot of the process industry in Norway has demographic challenges. Demographic, that means that we are a lot of old people that will retire in the next five years. And quite a few of the process industries, they lie in areas with demographic weak development. That means that we will have to compete about talent much more than we have did previously. There are regional capacity challenges. There are higher turnover coming, and we also have gender challenges. In fact, my own company, Hydro, we only have about a little bit more than 20% female employees in our company, and that's not good enough in the future. We need to recruit from both parts of humanity. I think these are challenges where we need to really point out that the future of industry is not necessarily in all these new batteries and hydrogen and so on, but the traditional industry also has a great future. We can do that together, and we have some assets in Norwegian industry, but it doesn't happen by chance. We have innovative and competent operators. When I've been talking, I've been engaged in some of the battery initiatives, and when we've been talking to some of battery plants in the US or in Japan, they are always very impressed about the competence of operators in Norway and how they work on their own without supervision. They are innovative and competent. We have engineers that are used to work on shop floor. That's not the case everywhere in the world. Sometimes they enjoy more being at the office than at the shop floor. But we have a very close cooperation with that. We have abilities to do step changes rapidly also. We have studied this in research program and seen that that is really an asset for many companies in Norway. And that has to do with the previous one. We have also an educational system that is quite responsive to cooperations between industry, education, and also trade unions. I think that's also something that we should exploit even more, but then we need an arena to do that in, and where DigiPro could contribute. And we have, as I mentioned, also a third-party cooperation. We are pretty low on conflict level in Norway in the industry, and both trade unions and industry have that in common, that they want to develop their people and give people the chance to develop further. Battery growth needs organizational capacities. That's also something that needs to be done without cannibalizing the existing industries. Battery industry is a combination of process industry and manufacturing industry. We have both in Norway. We have high-speed manufacturing and automotive suppliers in Norway that we could capitalize on, and we have a good process industry, but they need to cooperate. So we need cooperation rather than competition nationally in Norway. And that's why we also have launched a project in Norsk Industri, which will be presented on Wednesday. So if you are interested in competence and the battery industry of Norway, there is a webinar on Wednesday between 10 and 12 on battery industry in Norsk Industri homepage. That project will identify gaps that needs to be mitigated with regards to competence. Competence, capacity, and organizations makes capabilities, we say organizational capabilities. I must also say that, unfortunately, some governmental bodies have been dragging their feet in this respect. So this project has been funded by Norsk Industri without the support of governmental funding. Digital transformation is essential for sustainable growth. However, digitalization will not succeed without the organizational part. As Trygve pointed out also, we have the technical part and the human part needs to work very closely together in order to get a digital transformation. This slide I borrowed from SINTEF. It's about the operator 4.0, which says that we need to give the operators technology that could really help them do their task much better. We have the augmented operator. They have pointed out they've used just some nicknames to the different types of operators. One is the augmented operator, the analytical operator, the smart operator, the social operator, and the super strong one, and the healthy operator with wearables, and they also have the collaborative operator. This sums up, I think, different digital helping tools that should be provided for an operator in a high productivity industry as we need in Norway. I will tell you a little bit from my own company, from Hydro. We have digital tools that is in the process context and that thereby amplifies learning. Safety is, as you know, is always a challenge in industry. We don't want people to be hurt at their job. We don't people It could go even worse. I've experienced that myself when I worked at the plant, and that's not something that you would like to experience. But safety is very important. Therefore, we have developed what we call safety skills. Safety skills training and testing on mobile phone platforms for all in aluminum metal and also for visitors, where they use a cell phone for going through training material and also testing before they are allowed to enter the plant. At the same time, we also have what we call safe behavior, where we utilize serious gaming technology to train in dilemmas that faces operators on a daily basis on shop floor. It's very connected to team discussions. It's a kind of input to team discussions, this safe behavior game that we have developed also. We had a research project together with Cybernetica, among others, and SINTEF, which was called Accelerated Learning Through Technology. I presented that previously at research conferences, but also for industry, but where we used serious gaming to play the heat balance process in the smelter. A complex process, and where we would like people to learn it rather in a gaming context than doing it in the cell. We use this very intensively particularly with apprentices, and I think we see a very rapid learning curve connected to gamification. A fourth initiative is what we call team performance, where we use tools for more precise feedback to the operators, and also on team execution of tasks, because in the electrolysis particularly, we need to have precise feedback on the different activities that you do in the continuous process. This has shown to be a very strong tool for the operators when they get very precise data back, and data that is connected to their daily tasks, because then they are able to see the gap between the different outputs in the team and also between individuals. I will tell you a little bit about that. It has been developed at Sunndal plant and in Høyanger plant. As you know, the continuous process in electrolysis is regularly given inputs that can increase variability in the process, like anode setting, for instance. And therefore, we need a very good precision from the operator to reduce the human variability of the tasks. Faster feedback from process and better predictions is data that they need to have in the context of the daily tasks at the shop floor. Precise feedback on precision level is given to the manual operation, and therefore they are able to systematically improve their tasks. So we sometimes call it democratization of trusted data, because it is given to the operators where they need it and when they need it. Team performance we have developed over many years with with digital process PIs, like you see here. We use the A3 method for the teams. They develop their own, each team of 5, 6, 7 people develop their own A3, which is built on analysis that they are supported with from the process engineers. And then they reduce the variability of the PIs over a period of 5 to 10 weeks, whatever it takes. And then we also see that they use these data to upfront of their shift to say that we know how to focus on this precision of that particular task. As we have seen, the variability has been brought down, but it's not sufficient. So this gives the right discussions for the shift teams too. This requires quite a lot of leadership development too, because leaders need to support this and facilitate this kind of processes in the teams. We also acquire research-based knowledge in the making of these digital support for operators as well as a whole organization. Because utilizing old and setting up new connections, we need to cooperate with SINTEF, with NTNU, with Kybernetica, and we also use quite a lot of a serious game company called Attensin, which is a Norwegian company. Now we have currently the Lean Digital research project, where we see what we call the Lean digitalization paradox, which is the starting of it, where we work and see how could Lean be enhanced and amplified through digital support. We previously had 2 research projects on this, which I mentioned, accelerated learning through technology, but also the research projects called Step Changes in Mature Production Systems. We even have consulting companies with us in this, like it is in DigiPro too, with Deloitte. And we cooperate with Bentler, which is at Raufoss, the bumper beam producer. Equinor is also part of it, and Kværner, together with NTNU, SINTEF, and Hydro. So, digitization as competitive asset was my starting point. And I would say the conclusion so far is that the answer to that question mark is absolutely when put in the right concept. It's in giving better data to the operators, is connected to competence development process, which needs to be a very strong and systematic process. It's combined with right organizational setup and needs to have a clear business case. And also the partnership in learning with other companies, I think it has been very valuable for us in developing this at Hydro. And where we also have researchers understanding what business we're into and giving result as we go along. So it's not necessarily something that is going to happen in 5 years, but that where we focus also on lower hanging fruits in the cooperation. I would say that if we can do it this way, then it gives digital transformation on our way to what we call incredible productivity, which we need to have industries in Norway. But there are still lots of challenges we can solve together. So, thank you.
Okay, thanks a lot. Do we have any questions for Per? Okay, so
you have to take yours.
No, but I was hoping that this was so interesting that there's a lot of questions. But I saw the concept of operator 4.0 with augmented reality and big data analytics operator.
Yeah.
Very interesting, and also with gamification.
Yes.
So, what would you say is the best starting point? If you want to, okay, I was inspired by your talk, where do we start?
Well, we always start with the business case, that there's a business case in this, because that drives motivation for people. And that creates also motivation for managers. So in a way, it needs to be a clear business case to it in the making of it. I think that's a vital starting point.
Yeah.
And then there's a lot of other things too that comes after that. Yeah.
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 Okay. Yes, please.
Thank you. My name is Anjas. I represent ASPIRE, which represents 10 sectors of the process industry. What are the main difficulties that you have faced to implement these skills? We know all the sectors tell me they have a shortage of people ready in IT. So what are the main difficulties you have faced here?
Well, definitely.
Could you repeat the question?
Yeah. You asked about the main challenges or difficulties in embarking on a road like this. I think in our industry, or in my company at least, we haven't seen this. The lack of digital motivation as a kind of blocking thing, because I think when it's connected to making life better and more precise than it was previously, then it's very easy to have the motivation of people with us. But if I should talk for the whole national level in Norway, I would say that we need a much more competence at university level, at operator level. We need to be much stronger on that. But I think we have the threshold for people going into such things is pretty low in Norway, because I mean you cannot even get your salary, or post offices doesn't exist anymore in Norway. You go to and so we have come pretty far on the digital tools that we use in the daily life. So I think that's the threshold that we need to pass. Is at a very low level, low entry barrier for us, so to say. So, but indeed, we need to at all levels to increase the amount of digital competence, and also to have a very clear business case like I mentioned, for the projects that we're running. I don't know if I answered your question, but yeah.
Okay.
Okay.
Okay, over there.
Within Hydro, which is my main.
So the question was.
I'll repeat the question.
Yep.
Yeah. Where are the Norwegian companies in comparison with other countries? I think that if I take my knowledge mainly from Hydro, I would say that we have come pretty far on that. I know that if you take the Norway, Sweden, and Finland, I think they are at the forefront of this, and we've seen that when we have been investigating where to put new type of industries, for instance, battery industry, that they are at the forefront of that. Within Hydro primary production, we are pretty long. I think we
we have come quite far. Our company in Qatar, by the way, they are also very advanced in this because they could get people from all over the world, the best people from all over the world. And I mean, they have Indian engineers as operators. So I think that is also a very sophisticated company with regards to this, because they can grab people from all over the world. I think that we need in Norway, we don't have sufficient capacity, so we need more immigration in order to develop our industry, definitely, because there are so few of us.
Okay, I think that was a good ending. Competence is a key resource for us in the future. Okay.
Hope so. Yeah.
Thank you.
Thank you.
Okay. Okay. So det er alltid vanskelig å gjøre to ting på en gang, så jeg tar passordet først. Okay, so now it's time to shift gear a bit. We have been talking about the future and the arenas and now the competence. Now it's time to dig a bit into the technology. And our next talk is about a really impressive project that takes the concept of a digital twin even further by making them self-learning and forming a cognitive plant. Our next speaker has several years of R&D experience in energy storage, lithium batteries, fuel cells, thermoelectric generators, nanomaterials, high-density data, etc. Please welcome Senior Research Scientist at SINTEF, Akhilesh Srivisava.
Thank you. Good afternoon, everybody. It's a pleasure to be here, and I'm going to present one of our ongoing EU project. It's named Cognitwin. In this talk, I would like to introduce the project, and then you will know more about the results in those presentations which are lined up after the break. So before going deep into the project, let's start a quick introduction of Industry 4.0 and digitalization. It is believed that first industrial revolution started in around 1780, and the main driving forces were mechanization and steam energy. So what we did in first industrial revolution, it was mainly to reduce human efforts by machines. Then we moved to second industrial revolution, and that is about introduction of electrical energy and also assembly line. So the first assembly line by Henry Ford to produce cars in 1913 was also part of second industrial revolution. Then we moved to third industrial revolution, and we started to use more and more electronics, integrated circuits, PLCs, and computers. So many things have started to become automated in this industrial revolution. And currently, we are living in fourth industrial revolution, which is more about Internet of Things, connectivity, etc. So it is not only about connecting people, now we are connecting things as well. So when we talk about digitalization of process industries, here we are dealing with lots of data. They are acquired by a variety of sensors. So once you acquire data, you need network, you need data storage and processors. In last few decades, what happened that the advancement in network, data storage and processors have been incredible. Now we can find a processor with around 50 billion transistors. In terms of data storage, we are now talking about 1 terabit per square inch. In networks, we are living in 5G, and there we have started to talk about 1 gigabits per second. So the advancements in these sectors are not directly connected with process industries because they probably have demands, much higher demands from lots of other industries. But when we talk about sensors, they are directly connected with process industries because in some of the previous talks also, you have heard that we have harsh environment. In process industries, we might see very high temperature, corrosive atmosphere, magnetic field, vibrations, etc. So we have to find right set of sensors for those process industries. And once we receive the data, we are going to do lots of analysis, making twins and putting cognitive elements. Now coming to our Cognitwin project, Facts and Figures is a 42 months project. It's running from 2019 to 2023. We are currently at month 26 of the project. Total budget, 8.6 million euros. And we have 14 partners, 6 process industries, 4 technology providers, and 4 R&D partners. And they are coming from 7 countries. This project is coordinated by SINTEF, and it has 6 process industries: Hydro, Sumitomo, Sidinur, Elkem, Sarstal, and Noxel. We have 4 R&D institutes: DFKI, which is a German Research Center for Artificial Intelligence. We have Fraunhofer, of course, SINTEF, and University of Oulu. Then we have 4 technology providers: Cybernetica, Nisatec, Technopar, and Scotex. This project is an innovation action funded under one of the SPIRE calls from the European Commission. So the core objective of this project is, in this project, we are aiming to combine cognitive elements in the existing process control system so that it can autonomously act before any unintentional or unwanted process behavior occurs. And the key components in this project we are working at are sensor networks, digital twins, hybrid twins, and cognitive twins. We will talk about it later. Here you can see all the industrial sectors in SPIRE. So we started this project proposal by gathering a consortium from some of these sectors. So we have 1 engineering company, 2 non-ferrous metals, and 3 steel industries in the consortium. So these 6 process industries, they came up with 1 industrial pilots. For example, in non-ferrous sectors, Hydro is working with Gas Treatment Center, Cognitive Digital Twin. Elkem is working with optimization of silicon process. Then we have 3 steel industries. Sarstal is working with tracking system for rolled bars in the rolling mill. Sidinur is working with cognitive digital twin of a steel ladle. And Noxel is working with cognitive digital twin powered condition monitoring and control in steel pipe manufacturing industry. In engineering sector, we have Sumitomo, and they are working with boiler operations. So what we have done in these 3 sectors, we have built 3 work packages. So work package 1 is about non-ferrous, and work package 2 is dedicated to steel industries, and third, work package 3 is connected to engineering companies. Then we have found that which are the research institutes or technology providers which can be connected to these pilots. So here you can see how we have distributed the role of various partners for these industrial pilots. Now in this video, we would like to demonstrate the cognitive concept. Please have a look.
Process industry deals with very harsh environments. One of the main problems is the maintenance of the machines and the equipment working in such conditions. This is a story about a ladle used in steel production. It carries very hot steel, and the bricks on the inner walls are getting thinner over time. However, they should be replaced at the right time, not too early and not too late. Ladle is looking for solutions by defining the right timing for the brick reparation by using advanced digital twin technologies. Can a digital twin help the ladle? A digital twin is a formal digital representation of an asset that captures its attributes and behaviors suitable for communication, storage, interpretation, and processing. Ladle, could you help me? Digital twin. Yes, of course. I have several models. I can simulate your temperature in the next period. Have this model. Digital twin tries to get data from the ladle and applies it on one of the models. Ladle, could you tell me when I should repair the brick wall? Digital twin. Sorry, I cannot. I don't have the right model. Can a hybrid twin help the ladle? Hybrid twin extends the digital twin by intertwining different models to take advantage of both physics-based and data-driven modeling. Ladle, could you help me? Hybrid twin. Yes, of course. I have several models and will combine them in order to solve your problem. Hybrid twin tries to get data from the ladle and uses several models jointly. Ladle, could you tell me when I should repair the brick wall? Hybrid twin. Sorry, I can't. But I can predict that the bricks will start to degrade after 45 heating cycles. Although hybrid twin has a lot of different models, there are so many parameters which influence the wearing process, and some situations are not covered by existing models. Can a cognitive twin help the ladle? The cognitive twin is the next step in the evolution of the digital twin concept in the AI era by incorporating cognition aspects such as reasoning, planning, and learning. Ladle, could you help me? This is my last chance. Cognitive twin. I'll do my best. I've collected a lot of experience from human operators. Cognitive twin tries to get data from the ladle and compares with own models, including models of expert knowledge. Ladle, could you tell me when I should repair the brick wall? Cognitive twin. Yes, I can. I will use my cognition to prescribe optimal action. You should replace your bricks after 85 heating cycles. The solution for above-mentioned problems is the CogniTwin Toolbox, which will provide support, 1, from the detection of anomalies, 2, over the integrated prediction of unusual behavior, 3, toward the solution for unknown situation. It will be the result of the H2020 CogniTwin GA number 870130 project, which will cognify the process industry. Its goal is to enhance the potential of the process industry in Europe by creating and validating a new approach for cognitive digital twins affordable for all process industries. More information can be found at linkedin.com/company/cognitwin, twitter.com/cognitwin, www.cognitwin.eu.
Thank you. So in parallel to our work with all these pilots, we are also developing platforms or toolboxes. So in work package 4, we are working with CogniTwin platform sensors and data interoperability toolbox led by Nisatech. And in next work package, we are working with CogniTwin hybrid AI and cognitive toolbox led by Syntef. We are also working with Business Aspire Industry Impact and Exploitation in a work package led by Cybernetica, and communication, dissemination, and standardization activities are led by Fraunhofer. So in our general approach, how do we start with? So when we have industrial pilots ready, first thing we try to do is to know about critical quality attributes. So what are their targets? Here you can see a list, and maybe it's not all relevant for our pilots, but in general. So some of the industries might be interested in having better health and safety, environmental footprint, energy efficiency. They would like to improve their product quality, product yield, and innovate new products. In addition, industries would also like to reduce their downtime and waste. So once we know about their critical quality attribute, then we try to define key performance indicators. For example, a company is probably interested in reducing their emissions by 10%, or their energy consumption by 10% or 20%. So these KPIs are ready, and then we look into critical process parameters. A possible list could be temperature, pressure, current, voltage, and a lot more. So what we do, we try to optimize these critical process parameters to obtain the required key performance indicators for each of the pilot. Further, we start building twins, and before that, we have lots of modeling involved, and we have three-layered approach to define twins. We start with digital twin, hybrid twin, and then end up in cognitive twins. So what happens that as a scientist, I should believe that first principle models should always work. But in order to do that, we should understand these first principles quite thoroughly. And it's not always possible, particularly in the setup where we are dealing with large industrial setups. All the parameters, all the variables are not easily available. So what we do, we train our first principle models by data-driven models, and then we combine both into a digital twin. And we also have to make sure that they both are working together. So then we develop interoperability, and that is part of our hybrid models. And finally, it's not sufficient. So we would also like to know that what are the cognitive capabilities we can introduce here, like learning, detecting, adopting, exploring, reasoning, and optimization. So once these cognitive capabilities are involved, are included in the models, then we have our final cognitive twin ready. So in order to do all that, we are building a cognitive twin toolbox so that all the components are available. Current version of the toolbox is available at GitHub. So if you want to know more details about our toolbox and its component, you can visit this GitHub page. It is containing digital twin data acquisition tools and services. And here, when you go here on this page, it's just a screenshot. You can find all the links to know more and more details. It also has digital twin representation tools and services, digital twin analytics tools and services, and finally, digital twin visualization and control tools and services. So you can go on this page and know more and more details about all the components we are currently having in our toolbox. A number of public deliverables are already accepted by the Commission, and these are available on our website. So if you are interested in reading all these deliverables, you can visit our website and download these deliverables. Then very soon, we are going to put some of our public demonstrators' videos on our YouTube channel. That should be available within 1 to 2 weeks from now. So I invite you all to have a look on our YouTube page and see all these public demonstrators. So finally, our vision is Cognitive Twin will set a new standard for the design, development, and operation of the European process industry by introducing a platform that is going to integrate Internet of Things, big data, artificial intelligence, and machine learning. Thank you for your attention. And if you want to know more and more details, or if you want to be connected with us, you can visit our website, you can follow our LinkedIn page, you can follow us at Twitter, and YouTube page will be available quite soon. Thank you for your attention.
Okay, thank you. Are there any questions? So I'm always happy when you show a GitHub page. That makes me as a software developer happy. And I see that there's a lot of components ready-made. Do you think that the cognitive concept, is that something that companies should start investigation of themselves, or should we get involved into your project, the Cognitive Twin, if you want to learn more about this project?
Both. So you can get in touch with our project, and also sometimes cognitive elements are depending on your own pilots, like experience of the operator. So those kind of cognitive elements are depending on your own setup.
Yeah.
So we are open for both.
Good. And there was some questions earlier about, or some talk about getting from the piloting into the production. How do you think this will work with the Cognitwin? Are you know these projects, are they going into production or is it piloting you are doing?
We are just doing piloting.
Yeah.
But in future, our plan is to enhance the TRL level of these pilots and implement, but not in the scope of this project. But then we have to find spin-off projects.
Okay.
And then we will prepare exploitation plan during the project.
Yes. Okay. More questions?
Thank you for this wonderful explanation about this project. I would like to understand up to what TRL you will get with this project for this Cognitwin platform or mechanism or system, and then how far is this transferable to different sectors?
This one.
Could you repeat the question first? Yeah.
Okay. The question is about TRL level and our exploitation plan in a way. So we hope to go to TRL 6 here, and we will prepare exploitation plan. And our idea behind developing this toolbox is that we learn from these pilots, but our toolbox will be a generalized toolbox which can help a wide range of industries in Aspire sector. So it is not going to be limited to engineering, non-ferrous, or steel industries, but our toolbox will be applicable to a wider set of industries. Thank you.
Yeah. Okay.
My name is Petter, coming from Opti. You said something about the digital twin. Based on those results you get from the digital twin, how far is it? How far do you see beyond the digital twin so you can implement it into a real world, so you can run it by itself?
Okay, so the question was, if you have a digital twin, how far is it before you have a Cognitwin running on itself?
Yes. So Cognitwin will be ready in this project only. If you are talking about final industrial implementation, then we can say that we have to go some more steps in TRLs. So it's not final implementation.
So still learning.
Yes. Thank you.
Okay, then I think it's time for some 15-minute break with a coffee. But first, a small gift to you and a big applause to Achilles. Thank you. So we will start again 13:45. That's about 15 minutes from now. Da starter vi om 1 minutt. Ok. Da begynner vi. So, I hope you have filled up with another cup of coffee and ready to 3 more talks before you are able to have the next coffee cup. Okay, so data is the most important part in any digitalization project. And data is collected by sensors. And in the process industry, the sensors are put in demanding environments. Our next speaker, he knows sensors. You have probably used his sensors every time you deposit a bottle in a Tomra automat. He has been teaching and researching in universities in Oregon and Washington for years. Please welcome Anders Hansen, research scientist at SINTEF.
Well, thank you, and big thanks to Killers for a great introduction to the CogniTwin project, which I'll be also talking about, but coming at it from the sensor side of things. Sensors are, of course, the bedrock of the digital revolution, and the process industry rarely gives us pleasant conditions to work in. Demanding environments could be high temperature, it could be abrasive or corrosive, or mechanical hazards, and then there's dust. Dust is everywhere, and dust combines with all of these above. You have hot dust, abrasive dust, corrosive dust, and this is just a short list of the different harsh conditions that you could meet. You could have high pressure, high electromagnetic fields, radioactivity, and how do you deal with all these things? Well, there are a few generic approaches. In general, when you have a line of sight, you might use optical sensors. Optical sensing is a great way of keeping your sensitive technology at a distance, and you can set up a laser or a camera or some sort of device that'll probe the system that you're trying to measure. Sometimes you don't have a line of sight. You could try something like vibrations or acoustics, or measuring the motion of the system that you're measuring. You might try to put in some robotics or actuators to prolong the lifetime of your sensors, or prolong the lifetime or the interval of your sensors by being able to sort of dip them into the process. You could have trapdoors that open and close. Or you could put in some specialized interfaces, which is something that I would love to see more focus on, being able to separate, cut off your sensors from the demanding environment by, in this case, I've put in a viewport, but this could be any sort of interface that helps transfer information out to a safe location. And then let's not forget, sometimes you just have really, really robust sensors, because whatever your need is, chances are there's some company out there that delivers hardened sensors for high temperatures, for radioactive environments, for corrosive environments. Whatever it is, be sure to search the market before getting too sophisticated. Sometimes there's a solution there. And then, a line spaced apart, there's soft sensing. Sometimes you don't get a sensor in there, but you have peripheral data sources that you can put together. Each one may be only weakly correlated, but in total, they can be used to model up a relatively robust picture of the system that you're working on. And soft sensing has been a tremendous success story in recent years. Lots and lots of stories of how you can use existing sensor data to back out information you never could with an actual sensor. Though it's not my job to pick this apart, I do have to point out that these success stories are often the exception and not the rule, and often you really do need a real primary data source. One of the problems, well, here, let me, by the way, quote my thesis, my advisor and coworker, Marian O'Farrell, who had this lovely ramble a Sunday morning on LinkedIn about sensor data quality. You don't have to read all of it, but her frustration here is with the idea that, hey, here's sensor, we just use AI to bridge the gap between the sensor and what you need to know, no matter what your data says. And in this audience, this feels kind of like a straw man, because I don't think anyone here believes that you can take poor sensor data and just sprinkle magic AI on it. But it is a pernicious misunderstanding out there. And we're talking about science journalists, public policy makers, funding agencies who fundamentally misunderstand the importance of data quality of what's coming in. Often what they go to is these big tech companies. They say, look at this, you can use, as long as you have enough data, you can do just about anything. Amazon can tell you everything about you by your spending habits. The problem is that although modern process plants generate massive amounts of data, they don't generate data that is massively cross-correlated. So if some person in Australia decides tonight that they're going to watch, I don't know, Stranger Things, then in some tiny little way, that information is going to trickle into your recommendation list on Netflix. But process plants don't work that way. You have a limited number of data sources that are relevant to your environment, and because you don't have a true big data environment, you have to fall back, or not fall back, but you have to focus on data quality. So you have to protect the quality of those data sources you have available. And data quality can come in various ways. One is having downstream quality assurance, that is to have modules that assure that you don't have missing data, that your data is not unnecessarily noisy or outlying, that you don't have mislabeled data, and these are important in order to ensure the quality of a digital twin or a model or something. But what I'd like to convince you guys is that the real important thing is the physical understanding that comes with the sensor. Data quality begins with understanding your sensor, understanding the environment that it's going to go into, and understanding the interplay between these two. And this is a point that's so important that I'm tried to break it down into some categories here. This isn't canonical, this is my interpretation here. But basically you have, first of all, intuition. At a glance, does your data make sense? When you look at a graph, when you look at a picture, intuition ties in with one of the big challenges of the digital revolution, which is that trained process operators are so good at their job. And how do you transfer their sort of human trained perception into digital perception? And a lot of it has to do with a basic intuition for what you're looking at. Next, there's interpretation, which is related, the more textbook way, once you crack the numbers, does it make sense what you're seeing? And then on the other side of the coin, there's the engineering challenges. Can you engineer, can you design a sensor that gives you reliable data that you understand? Can you use digital feature engineering, also known as edge processing, to extract the most relevant parameters to help along the model that you're feeding this into? So a brief example, which is fictitious because I don't like talking bad about real companies. Imagine somebody wanted to measure the temperature of their molten metal. You could do this with, for instance, a thermal camera, but those are expensive, and someone realizes that thermal cameras just measure the intensity of the glow of what they're looking at, so why not just put in a photodiode? Costs nothing, fractions of a euro. So you do this, you hook it up to your PLC, next thing you know, you're collecting data, and immediately your intuition starts ringing. If this is the data over several batches, why is the temperature fluctuating by a factor of 2? What's wrong? Well, you set up a calibration measurement. You would have to calibrate the sensor anyway, right? And you see the temperature doesn't really change that much at all, but there's some sort of weird offset or nonlinearity in your data. Can you understand that? Well, yes, you can, because you call your favorite physicist. Your physicist tells you about the Stefan Boltzmann law, which says that the intensity goes as temperature to the 4th power, and all of a sudden your data fits. And knowing this beforehand saves you a lot of downstream artificial intelligence, as it were, which is a precious commodity. Then next you find out that the sensitivity of the sensor tends to vary with temperature, so you need to calibrate that. Then you find out that dust and smoke in the process is going to affect the sensitivity of the sensor. Then you find out that there are volatile substances, gases coming off of the ladle that is over time destroying your sensor. Can you ever trust the data from this sensor? So these are the challenges that you run into, and I'll skim this slide quickly, but what it comes down to is cost. Sensors are not cheap. If you want a data source that is reliable, that you can use in your model, then whether you like it or not, you're going to end up paying for it, and factoring that into your design choices is going to help you along a lot. So with that, I'd like to pop into some of the specific examples of sensor development that we have in the Cognitwin project. There are 3 particular pilots that have had interesting sensor development. And in no particular order, I would like to start with Sumitomo, the Finnish company that designs and deploys large-scale industrial boilers for power generation. Sumitomo has a problem which is common to a lot of similar systems, which is that fouling, that is deposition of material on the heat recovery surfaces, tends to destroy the efficiency of the plant. So the furnace produces all these tars and fumes, ashes, that'll settle like a crust on your heat recovery surfaces, and this is expensive to deal with. Sumitomo has a analytical model that they can use to optimize boiler parameters to minimize this effect, but they lack training data because they haven't been able to put sensors in there to measure the actual presence of this sort of fouling. So our challenge was to find out how we could do as direct as possible measurement. Immediately we saw that optical access was going to be hopeless. There's no way you can put a transparent optical surface, be it a camera lens or a window, into the flue gas pipe. But acoustics is possible. We can listen. And the sensor solution we came up with is taken from what's called modal analysis. It is a technique that's common in structural engineering and mechanical engineering, typically used to look for resonant modes that could be dangerous for a structure. That could cause, for instance, a car to start shaking and then, at worst, get into an accident. But we would like to see if we can use it to identify some of the resonant structures of the heat pipes. And as far as we know, nobody has tried doing anything similar, so this is quite a novel solution. The idea is that we take this shaker that you see here, in this case shaking a Volkswagen chassis, connect it to the steam pipes and try and set up some vibrations that you could detect with, for instance, an accelerometer. And this way you've removed the sensors through the flue gas walls to an environment that might be hot, but that is not corrosive. The data that you're seeing in the bottom here is from a laboratory proof of concept that we realized to demonstrate the viability of the technique. We see that both frequencies and amplitudes of the vibrational modes tends to change. In terms of data quality, we have designed a complex feature engineering system that uses both time domain and frequency domain features to really extract the interesting information from these heat pipes. Sumitomo has delivered simulations that give us a sort of textbook understanding of what we're seeing. And then there's an intuition layer to it because there are regular cleaning events, automated cleaning events that we can correlate with our data to see whether we're actually measuring what we think we're measuring. Next, Elkem is one of our pilots. They, of course, do work with molten metals, and one of their big challenges is that they have to do manual sampling. They have to send in human operators to collect samples of molten metal, which is a health and safety risk. So they want to know what sort of sensors they can put in to learn as much as possible of what they would have learned from that manual sampling, and preferably in an inline environment instead of having to bring it back to the laboratory. Their solution involves using thermal cameras, which can be used to monitor not just the temperature, but also using machine vision techniques applied to thermal video feeds, learn something about the chemical composition of the molten metal. The cameras have been carefully selected with, for instance, flame and smoke filters, and there's been a lot of dialogue with various manufacturers and vendors to find the best solutions here. And that's their first point in data quality assurance. Vet your vendors, find the best solution, use trusted technology as far as you can. Anything that provides an image is always going to be a good sensor because it provides the operator a visual interface where they can see very intuitively whether something is wrong or not. And we're taking advantage of certain physical features of the system. Elkem is using mechanical actuators as part of their engineering solution so that we can withdraw the cameras when there are events that might be hazardous to the sensor. And then, as I mentioned, in terms of feature engineering, we're using computer vision techniques to greatly reduce the data stream and make sure that we're only sending the most important information. And finally, the third pilot is Hydro, which of course produces aluminum. They use a process that generates large amounts of hydrofluoric acid, an incredibly toxic and corrosive gas that has to be filtered out in a gas treatment center. In optimizing the operation of the gas treatment center, they would like to know how much HF gas is flowing down the pipes. But how on earth do you measure something that literally eats up whatever sensor you put in its way? Well, Hydro had a previous experience with a Norwegian company called Neo Monitors, which produces gas sensors. And they had a solution that uses a two-layer protective interface. First of all, there are protective viewports made of very robust sapphire glass to protect the electronics, the laser, the detector from the chemicals in the flue. And also there's an air purging system that tries to prevent the atmosphere inside the duct from getting to the sensors at all. So with this two-level system, they hope to protect the sensor enough that it has long lifetimes. In reality, we've had some troubles with this sensor. Once because we installed the wrong viewports by accident, and that was a learning experience. Once because the purge air failed, and each of those show that we need the two-layer interface. Either one alone is not enough to protect the sensor. Finally, there's also the issue with alignment, which is very common in optical sensors, is making sure you've aligned all your optical components correctly. Like Elkem, Hydro chose a trusted vendor, in this case a Norwegian vendor, which has been convenient because you have a service apparatus nearby. They were very quick to deploy this sensor. It was chosen even before the project started, and we've been able to use the duration of the project to manage all the little things that come up, which is great, being able to do that during the project instead of having to follow up after. The instrument has built-in systems for exporting metadata that you can use for quality assurance and error analysis, and also here, like in the others, you have process events that you can use as a sanity test. If you can detect them, then you know your sensor is working, at least qualitatively. All right, that was what I had for now, and yeah, the real takeaway here is do not talk about sensor data like something that exists or doesn't exist, because sensor data is colored by all sorts of quality parameters, and those quality parameters are going to propagate up through your system and affect the quality of your final solution. So let's talk about sensor quality and sensor data quality. Thank you.
Thank you. So that was an interesting talk, especially about, you see, from a software engineering perspective, we dive into the system and we sort of stop at the sensor level. And yes, good to know about quality here. Do we have any questions regarding the sensors? So, okay, we have one there.
Oh yes, that's.
Okay, so you measured some gas. What could you explain that again?
You're referring to the hydropilot where we're measuring with a laser system. That's HF, hydrofluoric acid. This, incidentally, is the gas that made Årdal famous for all its trees dying back before they were able to filter it. And that is the challenge, to be able to measure its concentration. Okay, your question is whether we have also measured the output, that is, the emissions from the gas treatment center, which of course is there to remove this HF. And that is not part of the Cognitwin project, but it is absolutely something that's done, because there are strict environmental regulations on emissions of these toxic chemicals, and Hydro has to report them, and they have to know how much is happening, and that has been implemented in previous projects.
Okay. Thanks a lot for this talk. Okay.
Thank you.
Thank you. Okay. Let's assume that we now have collected data, and lots of data, and of course data with gathered with high quality sensors giving high quality on the data. You might have thousands of sensors, each generating enormous amount of data. How do you find the hidden gold inside this? I'm pretty sure that our next speaker will use mathematics to find it out. He has a PhD in mathematics, and he's been working with analytics and artificial intelligence. Please welcome Sølve Eidsnes, research scientist at SINTEF.
Thank you. Sølve Eidsnes, a small correction. I will talk about how my group in SINTEF Digital, the Analytics and Artificial Intelligence group, work in general with the process industry. And as you know, industrial reality is complicated in general, and also when applying machine learning to it. And a lot of these issues has been mentioned in the previous talks today as well. So I will go quickly through them, but we have big and complex systems. They're often quite old, and there is not a lot of standardization in the industry. The data quality is often poor, and we also deal here with often with safety critical systems, which adds extra requirement to to the precision of the results, but also the trustworthiness of the models. So this is a simplified work stream, and this is the way we work when we do projects with industry partners. So we divided it into 4 parts here. We start with the problem definition, working that out together with the customer. And then we get the data and we start assessing that and get help from the customer in understanding the data. And then we do the modeling. And the last part is implementing the models into the systems. And that is, of course, very important, and it has been talked about previously today. But this is not what I will focus this talk on. I will focus it on the first 3 parts here, problem definition to the modeling. This figure here is from a project we are doing, where we can say that these first 3 parts are in the green boxes, and then the implementation in the system is connecting these green boxes with the rest of the system. And this is, of course, important for us too. We want our models to be implemented and used and create value for the customer. But for reasons of time, I will stop at the modeling part here. And I will use this chart to try to explain a bit more about how we work with the customers. So when the industry partners come to us and they want to collaborate with us, they can be at different stages on this chart. They want to get to this point a good AI solution for the problem, but some of them might be down here. They come to us and they say that we want AI because our competitors have it, and they don't really have a lot of knowledge about AI, and maybe they don't even know what problem they want to use AI for. And others may have some data and they have an idea of what they want to do, but they don't know a lot, and maybe they know a little bit about AI, and maybe they don't know anything. And then there are those who have a good idea of what they want to do. They have a lot of data, they know what the data represent, and they have some idea of AI. And maybe they have even done a lot of modeling already, but now they are stuck, and they want our help in getting to the end point where they have a good model. And getting up there, it doesn't really follow a straight line, and it takes time and effort also from the customer's side. And if the customer is down there to begin with, then we have to spend some time in the beginning to talk about AI in general and how it can be used and what it can be used for. And then we want to spend a lot of time in getting a good understanding of the problem. So here we work with the customers so we can get up to a high level of understanding, of problem understanding at an early stage before we start to do a lot of modeling. And there will be iterations here and lots of rounds of discussions to work on the problem definition together with the customer. And that is also the case after we start doing modeling, or at least start looking at the data. We'll probably have to go back and redefine the problem. And in a collaborative effort, hopefully we will get to the end point together. And I want to emphasize this iteration on the problem definition. So if we go back to this previous simplified workflow, where we start with the problem definition. When we start discussing that, we want something that adds value to the customer, but also something that we see as feasible to do. And then there is iterations on that and discussions. But then when we start getting the data, we look at that and assess its quality, and then we have to usually go back and think about the problem definition again. Do we have the data to do what we wanted, or do we have to maybe look at other problems or redefine the problem a little bit? And this is this is also true when we start doing modeling. then maybe we have to assess if we actually have the data to get the results, or maybe we can gather more data or different data, and maybe we have to go back again to the problem definition. This could be that we can't do what we wanted, but it can also be that we understand more about the system, both from our side and also maybe from the customer side. That can change the definition of the problem. And I will illustrate this with a specific project that we are doing, which is on the treatment of wastewater. And this is a project that is similar to what we will do with, what we do with the process industry. This is a very big and complex systems which involves processes that are physical or chemical or biological. And when we started on this, we decided early on that SINTEF would be responsible of creating a flow chart of the whole system. And they had some flow charts and maps from before, but they were only on parts of the system, or they were too general, and they weren't serving our cause. So we made this flow chart in collaboration with the customer, of course, and then we put emphasis on recognizing where there was data in the system, and then understanding what this data represents, and then mapping that to the text that the customer use in the system, so that when we got the data, we know what this is in their physical plant. And this figure here is just a small part of the system. This is the first case we started on. It's a biological process. And quite early on, when we started working on this, we saw that we had to change the definition of the problem. This is a very complicated process, and as we presented early results, they weren't really modeling, but just data analysis. The customer saw interesting things there that changed the definition of the problem that we are doing. And a lot of what we do is challenges or problems related to data. And this could be dealing with getting data, or when we're having data, to how to deal with that. So often we don't have what we would need in a model. Maybe it hasn't been measured, or what has been measured by the customer is of value to them, but not really what we need for a model. And in some cases, it's not even possible to measure, or we have to figure out if it's possible to measure what we need. And even when there is data, it can be very messy. It takes time and effort to sort it out and understand it. And here it is very important that we get assistance from the customer or the industry partner to avoid wasting a lot of time on that. And we have also had projects where the customer don't own the data themselves. They've outsourced some of the production and the data with it. And we have had cases where it was easy to resolve this issue, but we've also experienced that this became a big problem. And then when we have the data, the first important task is to relate this to the process in a correct way. And again, here it's very important that we have a good communication with the right people who have the domain knowledge. And then it's difficult to say at any point before we start modeling if we have sufficient data. So maybe we have to start modeling and then evaluate that. A typical problem with the process industry that we are working on is anomaly detection, and then we need to have enough. We need to have data with those anomalies and enough of that to be able to train data-driven models for that. And we can also use existing models and get data from that, feed that into data-driven models. But then we need more than just that. If we only have that, we can't get a better model than the model that we're getting data from. So we have had cases where a customer had an existing algorithm, and the data they gave us turned out to be from that, and then we couldn't improve on that with a data-driven model. And in general, it is difficult for data-driven models to get good predictions outside of the domain that they are trained on. They are very bad at extrapolation, but more suited for interpolation. So I will go back to this case with the wastewater treatment to illustrate a bit of these data challenges that we had there. So for this part of the process, the biological process that I showed the flow chart of, we got the output data from that. There are several process halls, and in each hall we have one set of input data. Then there are 4 different biological processes with 4 filters, and we got one data set for that, or the output of that. And our understanding in the beginning was that this was an average. But then when we looked at it, and we understood that it's actually successive recordings from the 4 different filters in this one data set. And they switch every 15 minutes, and our sampling frequency was 10 minutes. So we had actually twice as many recordings from 2 of the filters as the other 2. And we also saw big variations in this data, which indicated that there are actually big variations between the filters. And we had assumed to begin with that this would behave similarly, because all the input we had was the same for all filters. And then when we actually eventually got the data for the individual filters, we saw that also over long time periods there could be very big variations between the specific filters. And this meant that we had to go back and talk more with the customer about we have to change the problem definition. Now we have to model the individual filters, and that's what we are focusing on now, doing that based on the output from each of them and the new data that we didn't have to begin with, that can separate the different filters. And this is from the same project, but a different plant and a different part of the process. This is a problem that illustrates how we learn more about system when we do the modeling. So here we wanted to estimate the solids content in the fluid, so the customer could optimize the use of chemicals and be prepared for high precipitation. And the first results, we used data from approximately half an hour back in time, which was based on the time that the fluid used through the tank, based on the volume and flow. And then we got quite bad results, a lot of noise. And we saw that the problem wasn't with the model setup, but that there wasn't, the data we gave the model wasn't enough to get good predictions. And then, starting from the hypothesis that there is a residence time in the cleaning tanks that is much longer than this approximately half an hour, then we used input from the last 8 hours, and we got much better results. And this also is because the feedback from sewage treatment plays a big role. And this gave a big improvement in prediction, but it also gave knowledge to the customer about the system. A very typical challenge that we face when modeling systems in the process industry is learning in a closed loop. So in an open loop, as we see in the above figure, there you have the changes to the system that comes from the state itself, and you have the changes that comes from the controller, so F and G here. But then when we close the loop, we run into problems, because then the controller depends on the state, and then F and G here, both the parts that affect the state, or the changes in the state depend on the state, and we are not able to distinguish between them when we learn such a system. And this is a challenging task, and one possible solution is to run on an open loop in a limited time. We are working in our group on how to do this in a safe manner, so we can have a campaign where we gather data on an open loop, and then we can be able to learn how the process will behave with different controllers and without controllers. And another possible solution is something that we see as a possible solution on several of the challenges to data-driven methods, and that is hybrid analytics or hybrid models that has been mentioned earlier today. It has a lot of different names, including physics-informed machine learning or physics-informed AI, but it means combining the knowledge that you have about physical system with learning from data. And this is useful if you have a model that's incomplete or only for parts of the system, or even if you don't have a model, but you know structures in the system, like conservation or dissipation of mass or energy, or both. Or if you have controllers, like in the previous slide. And also if you know how the parts of your system are connected. And this can also give a guaranteed behavior that you can't get from data-driven or purely data-driven methods typically, like stability of the solution, or you can constrain your solutions to physically reasonable regions. And within this field, one of the newest developments are so-called port Hamiltonian neural networks. This is very fresh research and in an early phase still. And here I illustrate this with a simple example of tanks and tubes. And here we use that we know how the tanks and tubes are connected. We know there is a conservation of mass. We know that there is loss of energy through friction. And we know how the flow is controlled. And then instead of just using a pure model, learning this directly from data, we learn the different properties in different parts of this. And then we are guiding the learning of the model so we get better results. And we also get explainability of the model. So we can learn exactly what the friction is and what the energy is and so on. And this is a very hot topic now. It shows up in the Gartner Hype Cycle of Emerging Technologies for the first time this year. But we have been working with this since 2017. And we are very interested in discussing with the potential partners about new projects on this. So I will finish with these 4 points of recommendations. Define the problem and iterate on that definition, also after you start modeling. Know your data and share your knowledge with the analysts early when you're discussing the possibilities. Share your data, but also your time, so you can explain your data and be a part of the process. And find the appropriate milestones, define specific goals, and if you have some low-hanging fruits, maybe start with that. And if something doesn't, if you are struggling with a problem, maybe it's important to move on in time and see if you can do other problems. Thank you.
Okay, thank you. So, do we have any questions for this talk? Okay, Suri.
I'm not completely sure I understood the question.
Maybe it's a confusing question that I can ask you separately.
Yeah.
Okay, I think I got it. It was quite interesting, but I can't rephrase it. So it was regarding if you had enough data, would it then be possible to still develop the model without sort of going into the... yeah.
I mean, I must admit I haven't worked with this myself, but in general the problem is if the controller is affected by the output, it's difficult for a data-driven model just by itself to distinguish between what comes from the changes in the state and then the changes in the controller based on the changes in the state. And maybe, as you say, there was enough input. I must say I'm not an expert on this.
Okay, so it's an interesting and complex team to the artificial intelligence. So thanks a lot for your talk.
Yep, thank you.
Okay.
Thanks.
And I think our next talk will sort of continue on this, that just having lots of sensor data is not always enough. And tools like AI and machine learning could help you, but it is not the only solution. The complexity of a nonlinear process control is huge, and Cybernetica has developed solutions for this. Cybernetica is also one of the organizers of this event. Our next speaker, he founded Cybernetica in the year 2000. Before that, he spent almost 2 decades at SINTEF. He has a PhD in cybernetics. Please welcome Managing Director at Cybernetica, Peter Singstad.
Thank you for the introduction. So I'll continue a little bit where the previous speaker left off. I'll talk about technology. I'll talk about technology for supervisory control. And the applications I'm going to mention are on chemical processes, and that's where we have some rather mature applications. And after me, there will be 2 presentations on where we apply the same techniques in context of the Cognitum project. So that will be more under development. So I'm talking about supervisory control, and we all know about supervisory control. For instance, we have for several decades had autopilots for planes. We have had weather routing systems for ships. And now we are getting self-driving cars, or at least some dare to try a bit the self-driving properties of modern cars. And we are getting the first unmanned buses. All these are examples of supervisory control, and in Cybernetica we do not work with those things, but we do similar things for the process industry. So our mission is to develop supervisory control system for the process industry that have the possibility to learn from plant data, that have the possibility to adapt to changing process conditions, and that has the possibility to optimize the production on the run. And when we do that, it's important to maintain safety, a key issue, and it's the business case is that we can do this in a cost-efficient way. So we do this for chemical plants, as I will give examples on in this talk, and represented by this picture. But we also do it for metal refining, for primary metal control. We will have examples of that later on. We do it for aluminium electrolysis together with hydro. We do it for the energy sector, in particular the oil and gas industry. And we also work with amine-based CO2 capture technology. This represented by the Technology Center Mongstad, which is the big test facility for CO2 capture in Norway. So the technology I'm going to talk about is in a scientific term called nonlinear model predictive control. So it comes from a slightly different part of science and AI technology, but there are lots of similarities that I'm trying to illustrate later on in this presentation. And where we try to use knowledge from what I call here first principle models, which is knowledge on physics and chemistry. And it all starts with a model. It all starts with the tradition of Isaac Newton, it starts with physics, chemistry, and building on the systematic knowledge that has been accumulated by engineers, by scientists, through centuries after Isaac Newton. So we try to stand on the shoulders of giants, but still take advantage of modern data-driven techniques. So let me introduce the example that I'll be using throughout here, actually some variations of the same example. This is a chemical reactor. It's a batch process. It's strongly exothermal, and it needs accurate control. So when it starts with the model, it starts with formulating the model for the purpose of control. So we need to develop a set of differential equations, actually, for that process. And to do that, we need to know about the kinetics of the process. We need to know about the thermodynamics. We need to formulate mass and heat transfer relations. We need to know a bit about the mixing within the reactor. We need to formulate equations for the polymer properties, for instance. And we need to know sufficient about the rest of the production system, for instance, the cooling system, the feed system of reactants, and so on. And having done all those exercises, we typically have a set of differential equations, and we code that and plug that into our software. And we can take the first step into closed-loop control application. And the first step will then be to put the model online. So we typically put that on a server at the customer site in our software environment. And with that model in place, the model can calculate the same things as goes on in the process in a certain way. And when we do get data from the process, the model should be able to calculate a prediction of the same parameters. And what do we learn when we get to that point? What we learn is that the model prediction does not really give us the same answers as the real process. There's always a discrepancy. In addition, we have the benefit that we are able to calculate some states that are difficult to measure. But if we predict wrong, it has no value. So the next step is very important. And the next step is what we call a state estimator, which is really a data-driven technique. So what we do then is to take the model, we make a prediction, and then we measure, and we compare. And we see that there is a deviation. And that deviation we use an advanced algorithm to correct the model so that it fits better to the data. And those who are familiar with engineering cybernetics and control engineering, you would know that this estimator could be a Kalman filter or a moving horizon estimator. We use both in our technology. And the equations for that, I skip that in this talk, but they are there and they're well known and they work. Except we never stop at step 2, we never take that step alone. We do a slight twist to that always. We say, make a state and parameter estimation. So we, in addition to updating the states, we also calculate some of the poorly known parameters of the process, or parameters of poorly known phenomena that we know are there, but we don't know exactly how to model them. And that's when we move from a mechanistic type of model into a more hybrid or gray box modeling, some call it, because we use the data to learn from the process. And we can augment the model and use data to learn from that. I'll try to exemplify this a little bit, going back to the same reactor. In this reactor, there are certain things that we know quite well, and there are certain things we don't know so well. We have, for instance, a good picture of the reaction kinetics. It's well known. It's been published 40 years ago. But we are uncertain whether plugging that into a big reactor model is really telling us everything we need to know. So we will add a correction factor for this reaction rate, and we estimate that from plant data. And here's the result. This is for a PVC reactor, not far from here. And we see that, well, we see a systematic variation. We have time on the x-axis here, and we have the correction factor on the y-axis. And we see that there is a systematic variation. So this parameter is clearly not a constant. It varies throughout the batch. And once we have seen that, we can understand that, well, this probably has to do with that we get some diffusion limitations in the reactor that we haven't included in our model. But it doesn't matter, because we can estimate this and we can use this in our predictions. Another example from the same process is that we can model rather efficiently the heat transfer from the cooling surface to the reactor. But we know that maybe that isn't the whole story. Maybe that heat transfer varies a little bit. We saw that when we did this work. And what we see, if we estimate the heat transfer, we see that it's very systematic variation. This is for a number of hundreds of batches. And we see it systematically goes down when the conversion goes on. And the reason for that is that we get changing viscosity with changing mixing pattern, and the heat transfer goes down through the reactor batch. So we could, of course, have modeled that. We know how the polymer properties influence on the viscosity, but that would be very complicated, and it's no need for doing it. So with these corrections, we are able to have a rather accurate model that we can use for predictions, even though we haven't used all available knowledge to build a very high fidelity model. And having gone through those steps, we get to a point where we can use this in online control. So we add a controller, and the purpose of that controller is really to manipulate the process so that we achieve what the customer wants the process to do. And let me summarize this a little bit here and now. So we have the model, and the model together with the estimator fits to the historic data. Fits the model to the historic data, so it looks at the history. And we have the ability to learn from the history. Then the controller looks into the future and optimizes the moves of the process in the future so that we achieve what the customer wants. So optimize the future is the purpose of the combined controller and the plant model. So I said I'll have some examples from chemical processes. So batch reactor control could be done at several levels. The first level would be temperature control. And temperature control has been done since the dawn of man, so it should be easy. It's not so easy when it's a non-linear batch control process where a lot of other things happen at the same time that influences on the temperature. And the temperature influences on everything that has to do chemistry. So getting control of the temperature really gives you control of a lot. So that's the first step, normally not the only step, but a very important one. Then, as a next step, in order to achieve a business case, maximization of the feed to speed up the process is a good is a second step, and it seems easy. It should be just to turn up all the handles and feed it in. It's not, because now we're talking about exothermic reactors. So if you do that, you will build a bomb. and you wouldn't build a bomb at an industrial plant. So you need to know how fast you can feed, and you need to know that very precisely. So that's a second step, and an important step, because it allows you to save money, actually. And then on the third level, we have the product quality control, where the property of the final product is controlled. So all these things in various combinations come into industrial applications that we are working on. So we're coming back to one of the examples. One of the processes we've been working on is the model predictive control of phenolic resin production, so this is a base catalyzed step polymerization, where the feed of raw materials is essential to maximize the feed without maximizing the heat of reaction, or keeping that under control in the future is a key issue. And the challenge is, and the benefits of doing precise control of this type of process is to get better control of the temperature and of the reaction rates. So there are more details on this particular type of applications on our webpage, which is listed on the bottom of the slide. When it comes to this type of polymerization, which is a condensation type of polymerization, for those who know this kind of technology, the key issue when it comes to polymer quality is to stop the process at the right time, because we are building molecules larger and larger as time goes by. And in order to tell the operator when to stop, we have built this system that we call an endpoint prediction system, where we compare the current batch under production with the best batch from the history, the golden batch or the fingerprint batch. And we do that in such a way that it's really comparable. Even though the current batch takes a bit longer or goes a bit faster, it should be comparable in time, so we can see when to stop the production. Now. And another example is on the non-isothermal polymerization of PVC. This is a free radical polymerization, where we have multiple phases and a rather complex chemistry, and where the production rate is limited by the cooling capacity. So in this system, we developed a solution with model predictive control in combination with dynamic real-time optimization. So we have a two-level approach where we optimize the temperature profile in order to utilize the cooling capacity at best as possible. And on the lower level, we implemented temperature control so that we were able to follow that very, very closely. And the result looks like this. We see that by doing this optimization, we could shorten the batch time a little bit. And we have other additional benefits from doing this. And all these benefits were not known when we started doing this work, but we learned on the way, and it all comes down to that we are able to produce the same quality with a shorter time and with less use of resources. So these examples, they are implemented in a number of facilities around the world, not on every continent, but on 4 continents, and as far away as New Zealand. We have no plans of going any further. And they run 24/7 and are in production all the time. So in summary, we have a technology that enables us to do process control for rather advanced chemical plants. Now in new project, we try to use the same technology in new areas, which we are going to hear about more later today. And our business idea is to do turnkey installation and offer full maintenance of the installed plants. So thank you for your attention.
Okay, thank you. So, do we have any questions for Peter? If not, I'm sure there will be more. If you have, you could also ask in the two next talks, because they will also be regarding the same. So thanks a lot for your talk. And of course, a gift for you too. Vær så god. Okay.
Thank you.
That's all. Okay. Now, let's dig into a use case for a hybrid digital twin. Our next speaker, she took her PhD in chemical engineering in California, and she has been working as a senior control engineer in Cybernetica for the last 2 years. Please welcome Sudhi Javaheri.
Thank you.
Okay.
Yeah, thank you so much. And also just thank you to all of you for being here and to all of the other presenters for their perspectives today. My name is Sudhi Javaheri. I work at Cybernetica with Peter and Kasper, who we'll hear from after this. And I'm talking to you today about a digital twin that has been developed as part of the EU CogniTwin project. So as part of this project, we work with mainly with someone at Hydro called Are Dyrøy, who couldn't be here today. So I will do my best to introduce the pilot case to you. The pilot case that we're working at is located at Karmøy Technology Pilot, so KTP. A few facts about it. It has 60 electrolysis cells that have been running since 2018 and produce an average of 75,000 tons of aluminum per year. And it had a successful performance test at the end of 2020, which means that it basically achieved Hydro's expectations for efficiency. The reason we work at KTP is because it's one of Hydro's most advanced plants, and a lot of its more than average number of digital signals are already available for us to use. So that's a good starting place for our work. So similarly to other Hydro plants in Norway and around the world, the primary process happening at KTP is primary aluminum production. But that's not what we're looking at. What we actually look at is a supporting process called the gas treatment center. And the role of the gas treatment center is to clean the fumes from primary aluminum production. And that gave us a really interesting opportunity, actually, in this case, because since it's not the core process, the GTC hasn't always been the first focus for digitalization and upgrades and development. And also, as Anders mentioned earlier, there was a new sensor that was planned for this project, and that gave us suddenly data that we could work with in a new way. So to break down some of the roles of the GTC, there are more roles. There are more ways that it functions that are not listed on this slide, but these are the things that we're interested in for our case. The GTC really starts at where the primary electrolysis process ends. So the primary electrolysis process is going on, making aluminum, and over the bath you have fumes that are emitted continuously. The first role of the GTC is then to suck out and draw out these fumes from the pot room so that you don't have unwanted emissions, unfiltered emissions through the roof, and so that you don't have a bad environment for the operators to work in. The next role of the GTC is to recover some of the lost material in those fumes. So in the fumes you have valuable and toxic fluoride. So the fluoride is valuable because you need to have a certain composition of fluoride species in the electrolysis cells in order for the primary process to work well. the fluoride is toxic because it's either in the form of hydrogen fluoride, HF, which, as Anders said, is really toxic, or it's in the form of a different species that can easily react to form HF. So that fluoride is desired to be recovered by the GTC. And then the last thing that the GTC does is it closes the loop, and it returns that fluoride that it recovers from the fumes back into the electrolysis process. So I will, all of these points I will explain a little bit more on some future slides. But to talk about where the digital twin has a role, it has a role in all three of those steps. When you think, so for the first step of HF emissions from the pot, it's an important role for the digital twin and any digital technology to be able to predict that level and anticipate that level in the future so that corrective measures can be taken before something undesired happens to the process. It's also important for the digital twin to be able to track the efficiency of the GTC as it recovers HF. So you want to track how much of the fluoride is actually uptaken in the process. And finally, the end goal of this process, the end goal of making a digital twin is to be able to more effectively close the loop and optimize the GTC production so that the GTC operation, so that when fluoride is returned to the primary electrolysis process, it's returned in a stable and predictable manner. And that's to ensure that the primary electrolysis process does not have a lot of disturbance variables coming in that strongly affect how well it performs. And if you break down sort of how, sort of comparing to how Petter talked about in our last slide, which parts of a digital twin perform these different functions. The first two on this list with on this slide with predictions of HF emissions and predictions of fluoride recovery. Those two are handled by an estimator and modeling and estimation methods. The last part for closing the loop is handled by a controller with model predictive control methods. So the GTC at KTP is delivered by GE, and it performs several functions. So as I mentioned, the fumes are emitted from the electrolysis cells shown in the bottom right. Those fumes travel through the piping of the GTC and are fed into GTC filter chambers. And each of those filter chambers consist of an adsorption reactor and a baghouse filter. Those filter chambers, what they do is they expose the HF-rich fumes to porous alumina in a powder form. And because alumina is porous and has certain properties, what ends up happening is that the HF goes into the crystal structure of the alumina and is basically removed from the gas and becomes a part of the solid state material. The interesting thing about that is that the alumina is the raw material for primary aluminum production. So having gone through the GTC, the alumina is then sent to a secondary alumina silo. And in this secondary silo is stored and eventually sent back into the pot room. And in this way, it becomes an effective, basically natural mechanism of recycling the fluoride. Because the alumina was already on its way into the primary aluminum production. It basically just took a detour through the GTC in order to pick up the fluoride and return it back into the primary process. So data for this digital twin comes from 3 different places. One is the fumes, another is the filter compartments, and a third place is the silos at the plant. We have an HF laser that runs and picks up information about the concentration of HF in the fumes. The flow rate of those fumes are estimated. The temperatures of the fumes are measured both before and after an integrated heat exchanger. The silo levels and certain filter operation parameters are also measured and used for the digital twin. Because the fumes start in the electrolysis process, data from the pot room is also sent to the digital twin. Alumina, as I mentioned, is the primary process's raw material and is used in high quantities by the GTC. So alumina comes to Karmøy after having been processed at Hydro's bauxite processing facility in Brazil. And each shipment of alumina is unique in its own way. And they basically, any batch of this powdered material has its own specific properties that makes it better, worse, different for performance in the GTC. So on this graph is an example property. The orange curve is called LOI, loss on ignition. And what you can learn from the graph is that it's correlated with the normalized HF emissions. And so what that means is that we can use that information from the alumina certificate as a predictive input into our digital twin to help anticipate what HF emission levels will be. And the last crucial piece of information that we use for this digital twin is the weather. I will explain a little on the coming slides. It will be more clear why the weather is so important. But for now, just know that basically through this project, SINTEF has developed a weather API that makes it possible to access MET's online weather measurements. So for this particular pilot, the closest weather station that had the information we need is at Haugesund Airport. So with this API, we access weather measurements real time. And another thing we're able to do is access MET's weather model. So the same weather model that is accessed on your mobile phones or your computers or your websites when you look at IR. And this weather forecast is then something that we're able to use in the digital twin to anticipate how the behavior of the GTC will be in the future. So all of those pieces of information are collected on an OPC server and made available to the digital twin. And the information from the digital twin can be used in different ways. It can be visualized and then looked at by an operator who may decide what to do with the information they see, make a change manually, make a change to the regulation system. Or it can be combined with a process control scheme and used to control the process in an automated manner. So on this, the basis of the digital twin that collects all that information, forms predictions, is a first principles process model. And a schematic of the information in that process model is on this slide. Yeah, I see that some of the slides are hard to read because of weird formatting, but I hope that they're visible enough. In this picture, the control volumes in the process model are shown as perimeters with dashed lines. And within each of those dashed lines, there's basically a state which is associated with a differential equation that describes how it changes over time as a function of different inputs. The real process has many electrolysis cells and many filter chambers. But for the purpose of numerical robustness and data quality, we average the 3 minutes. We average these together and yeah, we average these together, and that works well. So I don't want to go into too much detail about the first principles model, but I do want to explain how the physical mechanisms that need to be captured in the GTC work. So the bottom right-hand corner, you see the 4 reactions that contribute the most to HF emissions. So volatilized and particulate species come out of the pot fumes, and then these species that include elemental fluoride, they react with water and they form HF gas. So that's where you see weather being relevant, because the pot, when the GTC sucks fumes out of the pot gas, out of the pot room, it also has to suck in air from the ambient environment. And when it sucks in air, it inadvertently sucks in ambient humidity. And that ambient humidity changes over time, so the progression of those reactions varies frequently and significantly. So those reactions are evaluated, and the emissions level of HF is calculated. The next step for the model is to calculate how much of those HF emissions are actually uptaken in the alumina adsorbent. The top right graph shows a simple adsorption model. So if you look at just one of those colors, you get a simple idea of how this works. What it shows is that as the partial pressure, so concentration of HF, the x-axis, increases, the uptake, so the amount of HF in alumina also increases until it levels out at a saturation level. But when you look at all the different colors, you see something more nuanced. And what that shows you is that as the content of water in the gas also increases, you're able to absorb less HF. And that's because water actually competes with HF to get into the pores in alumina. And so then you suddenly see that water is a distinctly nonlinear complicating factor in this system, because on one hand, when you have more water, you generate more HF that needs to be cleaned. On the other hand, when you have more water, you're not able to capture as much of the HF that you need to clean. And so that's a challenge, and it's a real challenge that the operators for the GTC have to deal with. So those absorption models are also evaluated, and the final predictions are made. So just really quickly, some results from this project. The blue graph here, the blue graph on the bottom shows the HF laser measurements from a stable period, and the pink graph shows model predictions. There are long-term fluctuations in this data, and those can be mostly explained by looking at the top graph, which shows you absolute humidity. Shorter-term fluctuations, so a lot of the apparent noise in this have to do with process data variations. As Petter mentioned, we use Kalman filters for adding a data-driven element to our work. So what we are able to do is look at the error in the model on the previous slide, the error between the measurement and the predictions, and use it to update our model and make it and improve it. And an example of that is shown here, where we basically have a parameter for our alumina performance, and you update that over time in addition to the model states in order to better follow the process measurements. And those are shown on the top, whereas the parameter that's estimated is shown on the bottom. And then, almost done. On this last slide, you see an example of what we're actually trying to control in this process. These two graphs are both examples of what the model predicts is the fluoride content of the alumina. And in the end, this is what we want to keep as stable as possible, because we don't want huge variations going into the electrolysis cells. So you see the model predicts if you change the operation of the GTC, you can achieve different amounts of fluoride content. So if you want to keep the amount of fluoride in the alumina stable over time, you have information about the future, the weather forecast, and the coming process data, You combine that with model predictive control, and you use that to optimize the recycle ratio so that you stay within the bounds that you defined for yourself. Okay, and that's my contact information, and I'm done.
Okay, wow. I'm sorry to stand there, but you are impressing how fast you could do the last slides. That's very good. Do we have any questions for Sudi? Yes.
So your digital twin is predicting a GTC. Does it also look into the water consumption of the wet scrubber?
No, it doesn't. That's
Could
not
you
part.
repeat
Yes,
the
the question was if this case looks into the water consumption of the wet scrubber. The wet scrubber is not looked at all, so I've never seen that data. That could be an interesting follow-up. Yeah.
Good. More questions? Yeah.
We heard earlier today how important it is to have the right data. And in machine learning, we see that it's one of the biggest parts of the work. It takes up easily 60% of development time just to do data management and feature engineering. How is it when you do a first principle model like this? What is the ratio like data massaging versus actually building the model?
You also know because you've seen some of the data, but also the question was with machine learning we heard about how important the input data is, and how do we see that same problem in our work? We do see the same problem in our work, that a lot of data is complicating to our work. A general rule we use is that when we make the first principles models, we have an expectation for how that data will come into our system. And while there might be biases and some issues with our models when we first build them, if we take an input parameter and we see more variation or worse agreement with what we're trying to model, then we often come to the conclusion that that data input was more harmful than helpful, and that we're not using it correctly. So that's something that has happened in this pilot. So not all of the data that we've had has been useful.
Okay. Okay, then time to some applause to Sudi.
Thank you.
And a small gift. Okay.
Thank you.
Okay, so now it's time to increase the blood sugar level. There will be coffee and also something to eat out in the hall. And we will start here 15:25. Okay, we'll start in 1 minute. Yes. Okay, so I hope you have enjoyed your small sandwich and got another cup of coffee. Our next talk will also be presenting a use case involving a hybrid digital twin. This time the domain is silicon refining. So our next speaker has been working for Cybernetica for the last 6 years. He took his Master of Science in Chemical Engineering in Trondheim. Please welcome Senior Control Engineer at Cybernetica, Kasper Linnestad.
Thank you. So my name is Kasper Linnestad, and I will be presenting our work in the Cognitwin project on an operator support system for ferrosilicon refining. And the project is, for this pilot, is a collaboration between SINTEF, Elkem, and Cybernetica. So the goal of this system is to improve the hit rate. That means that we are able to produce ferrosilicon at a given specification with respect to chemical composition. And we also want to maximize the remelting so that we recycle more material, which will increase the efficiency and the yield of the process. And in order to do this, we use model predictions, which will help the operators make more informed decisions. And we will also use these predictions to calculate optimal recommendations for the operators so that enable them to improve the hit rate and maximize the remelting as much as possible. So Elkem is a global producer of silicons, silicon products, and carbon solutions. And we are working in this project on the silicon product segment, specifically the ferrosilicon alloys. The plant we are working on as a pilot in this project is Elkem Bremanger, which is located in Svelgen on the west coast of Norway. And that plant has 2 furnaces that produces ferrosilicon alloys. So this is an overview of the system that we will create during the Cognitwin project. So we have the post-tap hole process, which is the process chapter that we are looking at in this pilot, which will be observed by a set of infrared cameras. And then we will develop a hybrid digital twin, which will read data from the process itself and also from the infrared cameras in order to make optimal recommendations, which will be presented to the operators in the form of a graphical user interface. So let's dive into the process first. The process consists of 3 steps. The first step is tapping the furnace. So molten ferrosilicon at around 1800 degrees is tapped from the furnaces at regular intervals into a transportable ladle. And there's about 5 tons of metal per batch. The second step is refining, where certain chemical elements are removed from the metal and into a slag phase, which is a liquid oxide layer that floats on top of the metal. Because the chemical composition of the metal that is tapped from furnace varies with the raw materials that are added to the furnace, some adjustments must be made to each batch, so no batch is the same. And also we are producing several different grades, which also needs adjustments. So we need to refine by adding oxides to remove certain chemical elements and also add other alloying elements to meet the required composition of that specific grade. After refining, the temperature is lowered and the liquid ferrosilicon is poured onto a moving belt with molds in which the ferrosilicon solidify. And after that, the solid ferrosilicon is then sent to a facility for crushing, screening, and packing, and then it's ready to be sent to the customers. So that's the process. In the Cognitwin project, we will install a set of infrared cameras to observe this process in order to gain more information. So you heard Anders from SINTEF talking about this earlier. And we will install one camera for each of the processes and combine all this data together with some advanced machine vision algorithms to extract as much useful information from the cameras as possible, and then utilize this data for the hybrid digital twin. So the hybrid digital twin consists of two parts: a data-driven slag model, which aims to predict the amount of slag that enters the ladle during tapping, which will be developed by Sølve in SINTEF, and combine that with a digital twin, which is based on a first principles model of the process. So we're using Cybernetica CNIT to implement this digital twin, which is a combination of a first principle model, a Kalman filter for updating the model in real time, and we combine that with a nonlinear model predictive controller to calculate optimizations for the operators to apply to the plant. So first principles model, for this case, is based on mass and energy balances. So we model 19 different metal species, 7 slag components, and we have a rigorous model for the heat transfer. So during the refining stage, slag is formed by adding a source of oxide to the metal. At Bremanger, we are using iron oxide, which will react with silicon in the metal to produce silicon oxide, which is a part of the slag. This silicon oxide is then in equilibrium with other elements in the metal, such as aluminium and calcium, and thereby removing these elements from the metal and transferring them to the slag phase. In addition, this process has excess heat, so we can utilize this excess heat by adding recycled ferrosilicon material to increase the yield and the energy efficiency of the process. So you got an introduction to the Kalman filter by Peter, and I'll repeat some of the information. So what we use in this case is that we have the model and the plant, and we run them in parallel with the same inputs, and we are calculating same measurements. So at the end of each refining stage, there is a temperature measurement, for instance, and we're also predicting the measurement, the temperature measurement by the model. And then we can compare these two and use the Kalman filter to update the model so that over time the process itself and the model corresponds as best as possible. So to summarize, we use the model to predict the temperature measurement. Then we take the actual measurement at the plant. Then we use the difference between the two to correct the model and update the parameters and the states of the model so that we get the best possible match between the plant and the model. The third part of our digital twin is the model predictive control. So we use the model predictions to look into the future and see what will happen under the current conditions. And then we combine this with an optimization algorithm to calculate the optimum set of changes to the plant to reach the desired goals for the process. So in this case, we want to achieve the correct chemical composition of the metal, and also we want to utilize as much recyclable material as possible. That's our goals. And we will achieve this by adjusting or suggesting adjustments to the addition of the alloying elements and also recycled material that we add to the process. So this can also be summarized as we make a prediction, combine it with an optimization, do an adjustment to the plant, and then repeat that for infinity. So to summarize the model predictive controller, we want to achieve the correct chemical specification. We want to maximize the use of remelting, which will increase the energy efficiency. And we will do that by calculating the optimum amount of each addition. The final part of the system that we will create is the operator support system. That is the graphical user interface that the operators will interact with. So we plan on showing a set of trends for key process variables together with the resulting optimum additions from the optimization algorithm. And then by showing these together, the operators can make informed decisions. So I'll explain this plot here. So the plot is divided into two parts by this black vertical line. To the left of this line, we have historical data, both from the model and also showing the measurements together with the model. And to the right of this line, we have future predictions. And we plan to show two types of predictions in the same plot. One prediction where the operators takes no action, just runs the process as normal. And the other trajectory where we show what will happen if the operator chooses to follow the calculated optimum trajectory. And by showing these two lines together, the operator can directly compare them and choose the best possible action accordingly. And that's it for my project. So, any questions?
Any questions? So, you are developing this now, or have you implemented this before? Is it?
We have implemented similar things before.
Yeah.
And in this project, we have started implementations. So we have implemented parts of this already. So the digital twin is running online as we speak. Okay. And we're also calculating predictions. But we haven't yet come to the part where we do optimization.
Okay, cool. Good. Okay, so a small gift also to you. Thank you.
Thank you.
Okay, so then we have come to our final talk, and this will be about a big EU initiative that could help fund your next digitalization project. Our next speaker is a seasoned international collaboration leader. She's involved in technology and business development through multi-partner, multi-country, and multidisciplinary collaboration. She has an academic background in international relations, and she now runs the Spire Association, A-Spire. Please welcome Angela Orduna, Executive Director of A-Spire.
Thank you.
Thank you.
Hello, everybody. Thank you for still being here today until the end. So basically, yeah, I see better like this. So as he said, I represent A-Spire. This is an association that represents the European process industry and that currently runs the Processes for Planet Partnership with the aim to transform the European process industry. So what are we basically? I will go a bit quick through some slides because I feel probably it's a bit late. So basically we are the private partner of this partnership. The public partner is the Commission. And this partnership, Processes for Planet, which used to be called Spire under Horizon 2020, but it's called Processes for Planet under Horizon Europe, is part of Pillar 2 and of Cluster 4 of Horizon Europe, which is dedicated to digital, industry, and space. But we have connections also with Cluster 4. An important point is that we have now, the Commission has allocated 1.3 billion euros exclusively for projects, dedicated projects of Processes for Planet. This is 27% more than in Horizon 2020. We also have 2 new sectors, refining and pulp and paper, which we didn't have before. Very quickly, we developed a strategic research and innovation agenda. And then what did we do? So we said, we defined the ambitions first. So the first ambition is related to climate neutrality. The target is to reach to the net zero scenario. So the process industries need to drastically reduce CO2 emissions. The second one is on circularity. And then the target here is near zero landfilling and near zero water discharge. And the third one is on competitiveness. There are no jobs if the process industries are not competitive. The green industry without jobs does not exist. And then to develop this, we defined 36 innovation programs that include mostly technological aspects, but also non-technological aspects, like the framework conditions for the market or skills. But then Horizon Europe supports only up to TRL 7. In some cases, up to TRL 8. But our SRIA develops the scenario from TRL 1 to TRL 9. So we have 2 big initiatives, the Hubs for Circularity and the first-of-a-kind plant, to be able to support the industry to reach to TRL 9, to reach to the impact phase. I will explain about both later. So here, on these 36 innovation programs, when we talk about climate, we need to, the goal or what we intend is to move from fossil fuels to completely green energies. And this could include hydrogen, this could include bio, this could include a series of alternative fuels. But the question is how to deal with the energy mix and how to adapt the processes so that they are efficient with this energy mix. And then when it comes to circularity, then we are considering even more the full value chain. So here we have 2 big things. One is to move from the current scenario of incineration or landfilling to the future scenario, upcycling. That is keeping into the same loop the resources that will be in the right, with the right quality to be reintroduced in the process industry again, in the industrial processes again. But then a second one is the eco-design of the materials. And since we always work from a cross-sectorial perspective, when we refer to the eco-design of the materials, we refer to how the processes need to change so that these materials are produced in a different way, considering this eco-design. So let me go to the first-of-a-kind plants. What is this? These are the big plants. So when the big plants that will represent a complete novelty in the scenario of Europe on how the plants should work. So it could be a completely new big plant or a new unit within an existing plant that will allow to change the whole system and the way, the whole efficiency of the whole plant. So we have identified in our SRIA like 15, we call them marvels, metaphorically, 15 initiatives that could be taken into reality to change the scenario of the process industries. And then here we are always considering that a single technology cannot deliver the 100% emissions reduction. It's the integration of different technologies in these first-of-a-kind plants or units within a plant that can deliver that, but not a single technology. And then what about the hubs for circularity? In the hubs for circularity, we are targeting where the impact takes place. So we are conscious, and that has been a constant along all the Horizon programs of the Commission, that very often a project stops and nothing else happens. But of course, because impact only happens in a place. It doesn't happen just because a project finishes. So we need to take the projects to the next level. And then there is where we need things to happen in a region or in an industrial area, in a place where the industries are. So that, and then these industries cannot work only together. They need to collaborate, but not only together, they need to collaborate with the public sector, with the academia, with the research centers, also with civil society. It's very important to involve everybody in the decision making. So here we talk in the hubs of circularity of what we call the business to territory plans. So let's define what are the needs of the region, and then what are the solutions that we need. Some of them will come from the process industry, some of them will come from waste management industry, some of them will come from the municipalities. They will come from different actors, but we need to know what are the solutions, and then where are the waste streams, the energy streams, the data streams. Some of them will be here in Porsgrunn, for example, but some of them will come from other parts of Norway, or some of them will come from other regions in Europe. And that's what we need to identify, how to share all this information so that we all can grow together. We always say that the transformation that the European Green Deal, for example, suggests, and I see big similarities with this Process 21, is systemic. It's a whole system that needs to change, otherwise we will not have a transition. For this, we want to also create this European community of practice. This is already, there was a call, and we know that there are 2 projects that presented proposals there, so now we need to see which ones will be selected by the experts of the European Commission. And then the goal is to collaborate with the winning project and to create this European community of practice so that all this information is shared. And at Aspire, what we want is to be like the umbrella of the hubs. I see, for example, great options for a region like yours to become a hub for circularity. So this is much beyond the cluster culture. This is a systemic culture that we are looking for. And I see a lot of potential here, and it would be great that in 2 or 3 or 4 years' time, we can showcase your example as, hey, yeah, they are becoming a hub for circularity. That would be fantastic. But let me focus also on digitalization, because I know this is very important for Norway, and it's also very important for Processes for Planet. So in our roadmap, you can see there on my left, you can see the list of the innovation areas, and one of them is digitalization. But then for each innovation area, we have identified different innovation programs. In the case of digitalization, you have digital materials design, digital process development, digital plan, intelligent material. I'm not going to read them all, but basically, what we see is that digitalization affects holistically, horizontally to the process industry. So it's from the traceability of the materials to the process control to the integration of the whole supply chain, to the integration and the data and availability of the data on waste, on energy sources, so that you can really create a real transition. So we see digitalization as a great accelerator of all the rest of the innovations that we need to tackle, whether it's hydrogen integration, whether it's whatever. We need digitalization to accelerate. Here, just as an example, just as an example, here you have the calls of 2021 and the calls of 2022. You will see that there is no specific call on digitalization, but digitalization is everywhere. So that is the message I want to give to you. Any of these projects like CognicTwin could be in some of these calls. Of course, you need to look for the right one, yeah? But then digitalization is really something that we consider so important that it has to affect to all the calls that we have, or to most of them. I would also like to give you some examples of the Aspire projects that were supported on digitalization. So here you can see that so we have Horizon programs always have this work programming every 2 years. Right? So you see that every 2 years there was at least a dedicated call, in this case on process control or something related to digitalization. And there were 92 million euros dedicated exclusively to digitalization projects. But then this is just the dedicated one, because in fact, if we look at other projects, there's much more money dedicated also, but it's within other projects that maybe it's hidden, but there is. You see also we have, so CogniTwin is one of the result of one of the calls from 2019. And then you see, for example, also that we have another project, in this case it's a CSA, so it's not a technological project, it's more a coordination projects on artificial intelligence. Because when our sectors, by then it was 8 sectors, were talking, they told me, but Angels, we don't have enough expertise, we don't have enough talent in our companies on digital. Yeah, so I was very surprised today when they said, well, the steel sector it's not doing bad. Maybe globally, but what about in Europe? Is that the case also? Because that's not the feeling that we are having or what our companies are telling us. But that is to say that here, this is an opportunity to define what is next on artificial intelligence and big data for the process industry. And at some point, we expect to be able to showcase the results of this AI Cube project so that you can all share them and then maybe even contribute to the feedback. Then how do we work? That's an important point. I'm moving now to the way the partnership works. So you see that Aspire is talking with the public partner, which is the Commission, in the partnership board. So that's a space where Aspire and the Commission talk and define the topic. So in reality, what do? We organize this roadmap to influence on Horizon Europe calls. So we did contribute to shape the calls of 2021, 2022, and now we are already collaborating with the Commission to shape the calls of 2023, 2024. So this will determine what will be financed. And where do we discuss it? We have many informal conversations, but formally we discuss it in the partnership board. And then the European Commission or the European Union has this comitology process. So once we share a list and we share the content of the topics, then they discuss it with the member states in the program committee. And then it comes back to the partnership, to Aspire, and we give them back to the Commission. We discuss it in the partnership board. They discuss it with the member states. It's iterative until the topics are published. And of course, not all our suggestions are there, but many of the suggestions from our members influence what is there. And not only that, we see, for example, that a lot of our SRIA is in the Green Deal. We see that a lot of our SRIA is in several other of the policies of the Commission, of the European Union. So it's influencing. And this is not only with partners from the European Union, this is from members of Aspire, so including Norway, Norwegian members. Yeah? And then important, this is new, we didn't have it before, for the partnership in the current MOU, we have also an external consultation structure. So we have a feedback panel, and this is an option for us to discuss with civil society before, at the beginning, when we are doing the topics and say, are we forgetting something? Yeah, of course they will want to influence, but they don't have a validation role, they have a feedback role. And then, very important for the process industries, for Aspire members, we have an impact panel. So this is to support our members to move from TRL 7 to TRL 9. So what is the impact panel? It's a space of dialogue of Aspire members with the funders, with the member states, with the European Investment Bank, with other with the Innovation Fund, with other funders that are relevant to support projects like CogniTwin to move from TRL 7 to TRL 9 and then deliver impact. Yeah, so that is very important, and I think personally I have great expectations from this impact panel. Then how do we work? How do our members contribute to all these discussions? So there are several ways. So of course we have the typical General Assembly and the Board of Directors, but then we have also an advisory group. Currently it's called ERIAC, but then now this will change very soon. We have launched very recently a call to all Aspire members to present candidates to be members of the APG, Advisory and Programming Group. That will be the new name. But then also we have we will have a member states ambassador group. That is, we want in this group people who are well related with the member state representatives in our program committee or in our impact panel, so that when we send information, they can share and discuss bilaterally in their own language and then get to better understandings. And then also create this line of fluent communication between the partnership and between the member states, and Aspire, so that we can really align better with the member states. But then we can also influence on them. And then we have the experts groups, the Aspire working groups. I will move further on this now. So remember that we have identified the 3 ambitions. But then we say digitalization is transversal. Yeah, it's relevant to all of them. And then we say we have also some functional areas to tackle. We need to analyze the portfolio of Aspire projects. We have right now 141 Aspire projects. We will not have new ones because Aspire ended in 2020, but now we will have new processes for planet projects. So we need to assess what are the results of these projects. Yeah, what is the status? What is the future, the potential future of these projects? And then that is the function of the portfolio management. Then we also need to be aware of what are the technological trends or the business innovation trends that are out there, to see how to change our roadmap, how to update our SRIA, but also to see how to influence and how to shape the future calls. And this is the foresight teams. And then we need to collaborate with other partnerships. There is a landscape right now of 49 partnerships under Horizon Europe. We are not going to collaborate with the 49. I don't think this is humanly possible, but at least we need to collaborate with some of them which can be key to achieve some of the objectives. For example, the digital partnerships, just to put an example. And then here, for each ambition, we have created 2 permanent, we will create, because the call will be launched next week to all our members, 2 permanent working groups. So one on energy, another one on process optimization and CCU, another one on industrial urban symbiosis / hubs for circularity, one on resources and circularity, and then on competitiveness, we will have framework conditions and societal innovation. So that is more jobs, related skills, etc. Then we will have representatives of digital. Each of these working groups will have 1 leader, and we will have representatives of digital in each of the working groups. And then, depending on the working group, we can have several representatives of digital, meaning that they have some specific expertise that they can bring on AI, on big data, on cybersecurity, on Internet of the Things, on whatever needed, on sensors, that has been very much showcased today. Yeah? But then we will have also 1 representative of portfolio, another one for foresight in each working group, and then as many as needed on collaborations. So if we need to collaborate, for example, with hydrogen partnership, then this would be under permanent working group 1. But then if there are other partnerships which are relevant, these people should be people who are already in other partnerships, but then they are also in ours, and they can alert on the go and say, hey, we are also talking about this in this partnership. Why don't we create a synergy here? Or why don't let's avoid duplication, for example. So these are important roles. But then we will have as many experts as needed on all the different things that you see there at the bottom, or the different technological areas and many other that can be related to each permanent working group. Yeah? So that is the structure that we will create. Any new member of Aspire will be able to join any of these permanent working groups at any moment that they join, and to appoint 1 person per each group if they want. There will not be a limit. Yeah. And just to finalize, I would like to highlight a bit what is the added value that our members are saying that being part of Aspire has. It depends a bit on whether it's a large industry, an SME, or whether it's a research member. But basically, what the 8 sectors told me when I arrived here in 2017, is this continuous dialogue across the sectors has helped them a lot to learn about the common challenges and the common opportunities. And then to see also, hey, this sector is doing this, I am not doing it. Why? But this is very interesting. This could be transferred to my sector. What we are seeing now is that with the new roadmap, with the new SRIA 2050, new types of members are joining Aspire. And we are seeing that this dialogue in the very near short term and future will include not only the cross-sectoral dialogue of the process industry, but also the dialogue of the process industry with its suppliers and with its customers. And that is very important, because it means that we are also including more and more members of the value chain. And that is also very important for these circularity goals. As an example of activities that we do every year, you can see here, I will not extend much, but we do, for example, a brokerage event every year. Our brokerage event is this week, for example, Thursday and Friday. And there, any of our members can present a pitch. Hey, I have this project that I want to present in the next calls, and I'm looking for partners. Or the new members also can pitch, hey, I am new, and I have this expertise and this expertise. Or whoever can say, I'm interested in this call, and I'm looking to join any member who has a proposal on this call. Because maybe not all members showcase their pitch for the proposals that they will coordinate. But anyway, if they visualize the right member, they will contact them directly, and they will include them in their consortium, or at least in their conversations to create this consortium. That is all from my side. I hope I was not too long. But so thank you very much. And you have here my contact, so feel free to contact me at any moment.
Thank you. Okay, so do you have any questions for Angelica?
Angels.
Sorry. I did practice a few times.
You did.
And I was very good in practice, but well.
Yeah.
Okay, no questions? Then it's time to have to share the gift. It's
Thank you very much.
local produced
Good.
Yeah, cool stuff.
Very good.
Okay.
Thank you very much.
Thank you very
everybody.
much. Okay, big hands. Okay, so that was our last speaker. So this has been an amazing day with lots of interesting talks. And the official program. Tusen takk.
Tusen takk for hjelpen. Kjempegod styre.
Veldig bra. Takk. Okay, so the official program is now done, but there's no need to rush home. There will be served drinks and snacks out in the hall. Please continue the discussion there. And thanks to all of you spending the time with us. Thanks to all the speakers. And thanks to DigiPro, Cognitive Forsterk, Cybernetica, and SINTEF for organizing this event. Let's give them a big applause, and thank you all.